vastness of our universe, there exists a profound beauty in what we do not know. As you rest and listen, imagine looking up at the night sky, countless stars twinkling against the infinite blackness. Each point of light represents not just a distant sun, but a question waiting to be answered. Our journey begins here, in this moment of wonder, where curiosity meets the unknown. Science has always thrived on mystery. Every great discovery in human history began with a question, a puzzle that seemed impossible to solve. When Galileo first pointed his telescope toward the heavens in 1610, he revealed mountains on the moon and moons around Jupiter, forever changing how we understand our place in the cosmos. Yet for every question we answer, 10 more emerge from the shadows. The universe operates like an endless library, where each book we open leads to an entire wing of unexplored knowledge. We have learned much in our brief time looking upward. We know the sun is 93 million miles away. We know our Milky Way galaxy contains between 100 billion and 400 billion stars. We know the universe began approximately 13.8 billion years ago in an event we call the Big Bang. But what lies beyond these certainties? What secrets remain hidden in the fabric of space-time itself? These are the questions that keep astronomers awake at night, peering through telescopes, analyzing data, and formulating theories that stretch the limits of human imagination. Tonight, as you drift towards sleep, we will explore these cosmic mysteries together, not with the intention of solving them, but with the humble acknowledgement that some questions may take generations to answer. Others may forever remain beyond our grasp, visible only as shadows cast by the light of what we do know. There is a special kind of comfort in mystery. Unlike the uncertainties of daily life that may bring anxiety, the mysteries of the cosmos offer perspective. They remind us that we are part of something larger than ourselves, something ancient and ongoing. The same atoms that puzzle scientists today once burned in the hearts of stars that died billions of years ago, stars whose light is still traveling toward us across the immeasurable depths of space. Consider how remarkable it is that we can ask these questions at all. On a small planet orbiting an ordinary star in the suburbs of an average galaxy, consciousness emerged that can contemplate the birth of time, the nature of reality, and the fundamental forces that govern existence. We are the universe experiencing itself, asking questions about its own nature. As we journey through these mysteries tonight, we invite you to relax deeply. Let your mind expand like the universe itself, gently holding these cosmic puzzles without needing immediate answers. Feel the tension release from your body as you float among the stars, witnessing the greatest unsolved mysteries of space. The questions themselves become a kind of lullaby, a gentle reminder that not everything needs to be understood to be appreciated. Our exploration begins with something invisible, yet omnipresent, something that holds galaxies together, yet slips through our fingers like cosmic smoke. We call it dark matter, though we know neither what it is made of, nor how it came to be. Its mystery surrounds us even now, unseen but essential, much like the dreams waiting just beyond the threshold of consciousness. So breathe deeply as we venture into the unknown. Let these cosmic questions carry you toward peaceful slumber, where perhaps your dreaming mind might wander freely among the stars, touching mysteries that your waking thoughts can only glimpse from afar. The universe does not rush to reveal its secrets. Neither should we rush to understand them all at once. The beauty of the unknown awaits, like a cosmic lullaby singing across the vastness of space and time. As we drift through these mysteries together, remember that not knowing is not a failure of science, but its very engine. The questions themselves are precious, each one a doorway to greater understanding, each uncertainty a path toward discovery. Throughout human history, our greatest leaps forward have come not from confidence in what we know, but from humble curiosity about what we do not. When Einstein wondered what it would be like to ride a beam of light, he began a thought experiment that would revolutionize physics. When astronomers noticed tiny discrepancies in the orbit of Mercury, they uncovered evidence that would eventually confirm relativity. The mysteries we will explore tonight are not merely gaps in our knowledge, but invitations to wonder. They are cosmic koans, puzzles that may challenge our most fundamental assumptions about reality itself. Some may be solved in your lifetime. Others may require technologies and theories we cannot yet imagine. A few may forever remain beyond our grasp. reminders that the universe is under no obligation to make sense to human minds. Yet still we ask, still we wonder, still we look up at the night sky with the same awe that our ancestors felt thousands of years ago, before telescopes, before rockets, before we knew that stars were distant suns and galaxies were island universes swimming in the cosmic ocean. As you listen and drift towards sleep, allow yourself to embrace the mystery. Feel the weight of everyday concerns lift from your shoulders as your mind expands to touch questions of cosmic significance. There is peace in pondering the imponderable, comfort in contemplating the vast unknown that surrounds our small island of certainty. Now, let us begin our journey through the greatest unsolved mysteries of space, guided not by certainty but by curiosity, not by answers but by questions that illuminate the darkness like the very stars themselves. Imagine standing in a completely dark room, unable to see anything around you, yet somehow you feel the presence of something massive, something that affects everything in the room, including yourself. You can feel its pull, its influence, but no matter how hard you try, you cannot see it or touch it. This is the mystery of dark matter, perhaps the greatest cosmic puzzle of our time. As you drift deeper into relaxation, picture the universe as we know it, the glittering galaxies, the brilliant stars, the drifting planets and moons, the sparse dust floating between worlds. All of this visible matter, everything we can see with our most powerful telescopes, everything that emits or reflects light, accounts for merely 5% of the universe. 5%, a mere fraction of what exists. The rest, 27%, is what astronomers call dark matter. The remaining 68% is something even more mysterious called dark energy, which we will explore later. But for now, let us focus on this invisible substance that makes up more than a quarter of our cosmos. We first suspected the existence of dark matter in the 1930s, when Swiss astronomer Fritz Zwicky observed the Coma Cluster, a group of over 1,000 galaxies located about 321 million light-years from Earth. Zwicky noticed something strange. The galaxies were moving too quickly for their visible mass. According to the laws of gravity as we understand them, these galaxies should have been flying apart, the cluster dissolving like sand in cosmic winds. Yet they remained bound together, as if held by invisible hands. Zwicky proposed that some unseen matter must be providing the extra gravitational pull. He called it Dunkel Materie, German for dark matter. At the time, few took his idea seriously. It would be decades before the scientific community began to accept this radical notion. In the 1970s, American astronomer Vera Rubin made observations that could no longer be ignored. She studied the rotation of spiral galaxies, measuring the speed at which stars orbit their galactic centers. According to our understanding of gravity, stars at the outer edges of galaxies should move more slowly than those closer to the center, just as planets farther from the sun orbit more slowly than those nearby. But Rubin discovered that stars at the galaxy's edge were moving just as quickly as those near the center. It was as if our understanding of gravity was incomplete, or there was far more mass in these galaxies than we could see. The evidence pointed toward vast halos of invisible matter surrounding every galaxy, extending far beyond the visible boundaries of stars. Dark matter had announced its presence not through light, but through gravity, the one force it seems to exert on the cosmos around it. But what exactly is this mysterious substance? Despite accounting for most of the matter in the universe, we still do not know. We know what it is not. It is not made of the protons, neutrons, and electrons that compose ordinary matter. It does not absorb, emit, or reflect light. It does not interact with the electromagnetic force. It passes through ordinary matter, like a ghost through walls. The leading theory suggests dark matter consists of yet undiscovered subatomic particles. Scientists call these hypothetical particles WIMPs, or weakly interacting massive particles. True to their name, these particles would interact only weakly with ordinary matter, making them incredibly difficult to detect. They would have mass, and therefore gravity, but would otherwise remain hidden from our instruments. Deep beneath the Gran Sasso mountain in Italy, the xenon experiment uses tons of liquid xenon in an attempt to catch the rare moments when dark matter particles might bump into ordinary atoms. Similar detectors operate in abandoned mines in Canada, deep underwater in the Mediterranean Sea, and beneath the ice of Antarctica. These scientists are hunting for shadows, for the faintest whispers of particles that may constitute the invisible scaffolding of our universe. Other researchers suggest dark matter might be composed of axions, extremely light hypothetical particles first proposed to solve problems in quantum chromodynamics, the theory of the strong nuclear force. Still others propose sterile neutrinos, relatives of the ghostly neutrino particles that stream through your body by the trillions every second. Some more radical theories suggest we may be approaching the problem incorrectly. Perhaps dark matter does not exist at all. Maybe our understanding of gravity itself needs revision. Theories like modified Newtonian dynamics, or MOND, propose that gravity behaves differently over very large distances than our current models predict. Yet these alternative theories struggle to explain all the evidence that points toward dark matter. The evidence continues to mount. When galaxies collide, as in the famous Bullet Cluster, astronomers can map both visible matter and gravitational effects. These maps show the gravitational pull coming from regions with little visible matter, as if dark matter clouds passed through each other while the visible gas and dust collided. With gravitational lensing, we observe how light from distant galaxies bends as it travels to Earth, warped by the gravity of massive objects along its path. These observations reveal dark matter filaments stretching between galaxy clusters, a cosmic web invisible to our eyes but evident in its gravitational influence. Computer simulations help us understand how dark matter shaped our universe. In the beginning, tiny quantum fluctuations in the density of dark matter grew over billions of years, their gravity drawing in ordinary matter to form the first stars and galaxies. Without dark matter, these early structures would never have formed. Our Milky Way galaxy exists within a vast halo of dark matter, perhaps 10 times more massive than all its stars combined. Imagine it surrounding us even now, passing through the Earth, through your room, through your body, completely undetected. Trillions of dark matter particles may be streaming through you at this very moment, yet you feel nothing. They are ghosts made real, invisible to our senses, yet fundamental to our existence. In our own solar neighborhood, astronomers search for subtle effects dark matter might have on the orbits of planets and comets. Some have proposed that a dense region of dark matter, captured by Earth's gravity, might reside at our planet's core, undetectable except for the tiniest variations in gravity it might cause. The hunt continues in particle accelerators like the Large Hadron Collider near Geneva, Switzerland, where physicists slam particles together at nearly the speed of light, hoping to create dark matter particles in the resulting energy burst. So far, these experiments have not yielded definitive evidence of dark matter particles, but they have helped rule out certain possibilities, narrowing our search. Perhaps most exciting are the attempts to detect dark matter indirectly. When dark matter particles collide with each other in dense regions like the centers of galaxies or the Sun, they might annihilate and produce gamma rays or other forms of radiation we can detect. Telescopes in space search for these signals, these subtle hints of dark matter's presence and nature. Despite decades of searching, billions of dollars in sophisticated experiments, and the dedicated work of thousands of scientists, dark matter remains elusive. We know it exists by its gravitational effects, but its fundamental nature continues to hide just beyond our understanding, like a cosmic riddle waiting to be solved. As you continue to relax, consider this invisible presence all around us. The stars we see at night are mere islands in an ocean of darkness, not empty space, but space filled with something we cannot yet comprehend. Our visible universe is like foam on the surface of a deep sea of dark matter. We float atop mysteries far greater than ourselves. The quest to understand dark matter teaches us humility. After centuries of astronomical progress, after sending spacecraft to every planet in our solar system and peering across billions of light years with our telescopes, we find ourselves confronted with our ignorance of 27% of the material universe. It reminds us that science is not a collection of answers, but an ongoing process of questioning, a journey rather than a destination. Perhaps dark matter will remain mysterious for generations to come, or perhaps tomorrow, in a laboratory deep underground, or in the data from a space telescope, we will finally glimpse its true nature. Either way, its presence reminds us that the universe is stranger and more wonderful than we can imagine, filled with secrets waiting to be discovered by curious minds. As we drift from the mystery of dark matter toward our next cosmic enigma, Let your thoughts float freely in the vastness of possibility. Like dark matter itself, the answers may not be visible, but they exert their pull on our imagination, drawing us deeper into wonder and contemplation. As you continue to relax and drift through the cosmic mysteries of our universe, we now turn to something even more puzzling than dark matter. Something so elusive, so counterintuitive, that it challenges our very understanding of physics. Welcome to the enigma of dark energy, the force that makes up approximately 68% of our universe. If dark matter is a cosmic ghost, invisible yet detectably tugging on the visible universe, then dark energy is like a cosmic breath, gentle yet powerful, pushing outward on the very fabric of space-time itself. To understand dark energy, we must first understand a fundamental truth about our universe that shocked scientists in the late 1990s. The universe is not only expanding, it is accelerating in its expansion. For most of the 20th century, astronomers believed the expansion of the universe, which began with the Big Bang, was gradually slowing down due to the gravitational pull of all matter, drawing everything back together. It seemed logical. If you throw a ball into the air, gravity eventually slows it down and brings it back to Earth. Many scientists thought the universe might eventually stop expanding and begin contracting, perhaps ending in what they called a big crunch, the reverse of the Big Bang. But in 1998, two independent teams of astronomers made a discovery that would turn cosmology upside down. These teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying distant supernovae, enormous explosions that marked the death of certain stars. These particular supernovae, called Type Ia, always explode with approximately the same brightness, making them ideal cosmic measuring sticks. By measuring how dim these supernovae appeared from Earth, astronomers could calculate their distance. By analyzing the redshift of their light, they could determine how fast they were moving away from us due to the expansion of the universe. What they found defied expectations. Distant supernovae were dimmer than they should have been, meaning they were farther away than expected. The only explanation was that the expansion of the universe was not slowing down as everyone had assumed. It was speeding up. Something was pushing space itself to expand faster and faster. For this revolutionary discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. But what could be causing this cosmic acceleration? What force could overpower gravity on the largest scales? Scientists named this mysterious phenomenon dark energy, though the name tells us nothing about what it actually is. It remains one of the greatest unsolved mysteries in physics, a cosmic puzzle that may require entirely new understanding of the fundamental nature of reality. Let us explore the leading theories about dark energy as you continue to relax and let your mind wander through these cosmic mysteries. Perhaps the simplest explanation is that dark energy is a property of space itself. According to quantum field theory, even completely empty space is not truly empty, but filled with temporary, virtual particles that continuously pop in and out of existence. This quantum fluctuation might create a kind of negative pressure that pushes space outward. This idea connects to Albert Einstein's cosmological constant, a concept he originally introduced in his theory of general relativity in 1917. Einstein initially added this constant to create a static universe, one that neither expanded nor contracted. When Edwin Hubble discovered in 1929 that the universe was indeed expanding, Einstein called the cosmological constant his greatest blunder. Yet now, a century later, something very much like Einstein's cosmological constant may explain dark energy. If empty space contains intrinsic energy, a sort of vacuum energy that pushes rather than pulls, it could drive the accelerating expansion we observe. The more space expands, the more of this vacuum energy exists, creating a self-reinforcing cycle of ever faster expansion. However, when physicists attempt to calculate how strong this vacuum energy should be based on quantum field theory, they get a value that is wrong by 120 orders of magnitude, perhaps the most massive discrepancy between theory and observation in the history of science. Imagine predicting a person would be as tall as the entire observable universe, and you begin to grasp the scale of this mismatch. Another possibility is that dark energy is a new kind of dynamical energy field that fills all of space, but whose effect has only become important in the relatively recent cosmic past. Physicists call this hypothetical field quintessence, named after the fifth element of ancient Greek philosophy. Unlike the cosmological constant, quintessence can vary in both space and time. This might explain why the universe's expansion began accelerating only about 5 billion years ago, after spending the previous 8 billion years slowing down. Some theoretical physicists suggest an even more radical possibility. Perhaps our understanding of gravity itself is incomplete. Just as Einstein's general relativity improved upon Newton's theory of gravity, perhaps we need a new theory that explains how gravity behaves over the vast distances of intergalactic space. These modified gravity theories remain highly speculative, but represent another approach to solving the dark energy mystery. Others propose that dark energy might be leaking into our universe from another universe in the multiverse, a hypothetical collection of countless universes existing alongside our own. In this scenario, our universe might be just one bubble in a vast cosmic foam, influencing and being influenced by other bubbles in ways we are only beginning to theorize about. One particularly strange aspect of dark energy is that it does not dilute as the universe expands. Normal matter and energy spread out as space expands, becoming less dense over time. Dark energy, however, appears to remain at a constant density. As the universe grows, the total amount of dark energy increases, filling the newly created space. This is why its effects have grown stronger over cosmic history and will continue to dominate the universe's future. If dark energy continues to accelerate the expansion of the universe at its current rate, the long-term fate of our cosmos is one of increasing isolation. Galaxies outside our local group will eventually move away faster than their light can travel toward us, disappearing from our observable universe one by one. In the far distant future, perhaps 100 billion years from now, astronomers born in the Milky Way would see only a handful of nearby galaxies, with the rest of the universe having receded beyond detection. Even more dramatic scenarios are possible. If dark energy strengthens over time, a so-called Big Rip might occur, where the accelerating expansion eventually becomes so powerful that it tears apart galaxies, solar systems, planets, and ultimately atoms themselves. Alternatively, if dark energy somehow reverses its nature, the universe might still end in a big crunch after all. Our understanding is too limited to predict with certainty which cosmic fate awaits us. The mystery of dark energy touches on some of the most profound questions in physics. It may connect to string theory, which attempts to unify quantum mechanics and general relativity, the two great but currently incompatible pillars of modern physics. It relates to the anthropic principle, which suggests that the properties of our universe, including dark energy, must be compatible with the emergence of conscious life to observe it. Solving the dark energy puzzle may require entirely new physics beyond the standard model, which currently explains the behavior of subatomic particles with remarkable accuracy but says nothing about dark energy. Future space missions, like the Nancy Grace Roman Space Telescope, set to launch in the coming years, will map the distribution of billions of galaxies across cosmic time, providing more precise measurements of how dark energy has influenced the universe's expansion history. Ground-based experiments like the Dark Energy Spectroscopic Instrument, or DESI, will create three-dimensional maps of the universe, tracking its expansion with unprecedented detail. The Vera-C Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights for a decade, gathering data that will refine our understanding of dark energy. As we continue to probe this cosmic mystery, we are reminded of how young our scientific understanding truly is. Less than a century ago, we did not know there were galaxies beyond our own. Less than 30 years ago, we did not know the universe's expansion was accelerating. What fundamental truths about dark energy might we discover in the coming decades? What revolutionary insights might reshape our cosmic understanding? As you drift deeper into relaxation, imagine the vastness of a universe pervaded by this invisible energy, stretching the cosmic web ever outward, creating more space between the islands of light we call galaxies. Dark energy works silently, invisibly, yet it is the dominant force shaping the destiny of our universe. Unlike gravity, which draws things together, dark energy gently pushes everything apart, a cosmic breath expanding the lungs of space-time itself. The mystery of dark energy teaches us that even the void is not truly empty. that space itself may contain intrinsic energy and properties we are only beginning to understand. It humbles us with the reminder that after centuries of astronomical progress, we still do not know the nature of most of the universe. Yet this is not cause for discouragement, but for wonder and continued exploration. In the quiet darkness behind your closed eyes, as you float in the borderlands between wakefulness and sleep, consider that you exist in a universe more mysterious and wonderful than our ancestors could have imagined. The quest to understand dark energy continues, driven by the same curiosity that has always pushed humanity to explore the unknown, to seek answers to the deepest questions about our cosmic home. Now, as we leave the mystery of dark energy, let us drift toward another profound cosmic puzzle, one that speaks to our place in the vast and possibly teeming universe, in a galaxy of hundreds of billions of stars. In a universe of trillions of galaxies, where are all the aliens? Why does the great silence persist in a cosmos that seems ideal for life? This is the question we call the Fermi paradox, and it awaits us in our next exploration of cosmic mystery. As you continue to drift peacefully through the cosmic mysteries that surround us, we now turn our attention to a question that has fascinated humanity since we first gazed upward at the stars. Are we alone in this vast universe? This question leads us to one of the most perplexing paradoxes in astronomy, often called the Fermi paradox, or the Great Silence. Imagine a quiet forest at night. You know it teems with life, creatures of all kinds moving through the darkness. Yet as you listen, you hear nothing. No calls, no rustling leaves, no signs of the thousands of beings that should surround you. Such absolute silence would seem strange, even troubling. This is the cosmic silence that puzzles astronomers. The paradox is named after the physicist Enrico Fermi, who during a lunch conversation in 1950 reportedly asked a simple question: where is everybody? He was referring to intelligent alien civilizations. His question cuts to the heart of a profound contradiction. On one hand, the universe appears ideal for life. Our galaxy alone contains between 100 billion and 400 billion stars. Most of these stars have planets orbiting them. The Milky Way is just one among 2 trillion galaxies in the observable universe. The numbers are almost incomprehensibly vast. Even if only a tiny fraction of planets develop life, and only a small percentage of those evolve intelligence, the universe should be teeming with civilizations. Some of these civilizations would likely be millions or even billions of years older than our own. They would have had ample time to develop technologies far beyond our imagination, to explore and perhaps colonize large regions of the galaxy. Yet when we look to the stars, we hear nothing. We see no signs of megastructures reshaping star systems. No spacecraft from distant worlds visit Earth. Our radio telescopes detect no artificial signals from the depths of space. The universe appears eerily, profoundly silent. This is the Fermi paradox, the strange contradiction between the apparent abundance of suitable homes for life and the lack of any detectable evidence for it. To understand this paradox more deeply, we should examine what has become known as the Drake equation, formulated by astronomer Frank Drake in 1961. This equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of those planets where life actually emerges, the fraction of life that evolves intelligence, the fraction of intelligent species that develop technology capable of interstellar communication, and the length of time such civilizations release detectable signals. When astronomers input reasonable values for these factors, the equation typically suggests thousands or even millions of civilizations should exist in our galaxy alone. Yet we detect none. Why? Many possible explanations have been proposed, ranging from the hopeful to the deeply unsettling. Let us explore some of these possibilities as you continue to relax and contemplate the stars. Perhaps the simplest explanation is that we truly are alone, or at least exceedingly rare. Life itself might be common, but complex life could be extraordinarily rare. The evolutionary path from simple organisms to intelligence might require such a precise sequence of events that it has happened very few times in our galaxy. Consider Earth's history. Life appeared relatively quickly after our planet cooled, suggesting that simple life might emerge readily given the right conditions. But complex multicellular life took billions of years to develop. Intelligence capable of technology required another 500 million years after that. Each step required specific conditions and perhaps lucky breaks. The emergence of intelligence might depend on a long list of improbable factors: a large moon stabilizing our planet's rotation, plate tectonics, recycling carbon, and regulating our climate, a gas giant like Jupiter, protecting us from too many asteroid impacts. If true, we might be among the first or few technological civilizations to arise in our galactic neighborhood. Another possibility is that intelligent life tends to destroy itself once it reaches a certain technological threshold. This sobering hypothesis suggests that the same intelligence that allows a species to develop advanced technology also leads to its downfall. Nuclear weapons, climate change, artificial intelligence, biological weapons, nanotechnology, all these advanced technologies hold both promise and peril. Perhaps most civilizations do not navigate these dangers successfully. A different perspective suggests that advanced civilizations might deliberately avoid contact with emerging species like ours, a concept known as the zoo hypothesis. Perhaps they observe us from afar, waiting until we reach a certain level of technological or ethical development before revealing themselves. Like anthropologists studying an isolated tribe without interference, they may have ethical guidelines against disrupting our natural development. Some theorists propose that advanced civilizations might transcend their biological origins entirely, uploading their consciousness into computational substrates or evolving into forms we would not recognize as life. Such post-biological intelligence might have little interest in the physical exploration of space or communication with biological species. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests a more ominous explanation. Perhaps interstellar space is like a dark forest where predators lurk. Any civilization that reveals its location by broadcasting signals risks drawing the attention of more advanced species with unknown intentions. In such a universe, silence would be the optimal survival strategy. It is also possible that we simply have not been looking long enough or in the right ways. Humanity has only been capable of detecting radio signals from space for about 100 years, and we have only conducted systematic searches for alien communications for a few decades. This is a cosmic eye blink in a universe that is 13.8 billion years old. Our search methods might also be fundamentally misguided. We tend to look for technologies similar to our own, like radio transmissions. But a civilization even a few hundred years more advanced might use communication methods we cannot yet imagine, let alone detect. They might communicate using neutrinos, gravitational waves, or through principles of physics we have not yet discovered. Space is also unimaginably vast. Radio signals weaken with the square of distance, making them extremely difficult to detect across interstellar distances unless they are deliberately beamed in our direction. The signals we send out weakly into space would be nearly impossible for a distant civilization to detect unless they were specifically looking for them with extremely sensitive equipment. Time presents another challenge. Civilizations must exist simultaneously to detect each other. If intelligent life is rare but long-lived, civilizations might be separated by millions of years, ships passing in the cosmic night, never overlapping in time. Perhaps the galaxy has hosted many technological civilizations, but we are either too early or too late to coincide with them. Some astronomers suggest that truly advanced civilizations would not remain on their home planets but would expand outward, colonizing ever larger regions of the galaxy. Physicist John von Neumann described how self-replicating robotic probes could theoretically colonize the entire galaxy in just a few million years, a brief period in cosmic time. The absence of such widespread colonization might suggest that either expansion is not the natural tendency of advanced intelligence, or that such civilizations are exceptionally rare. Yet another possibility is that we have been visited, but in the distant past, before we could recognize the visitors for what they were. Perhaps evidence of these ancient contacts exists in archaeological records we have not yet discovered, or have misinterpreted. Some researchers even speculate that certain unexplained aerial phenomena might represent ongoing observation by extraterrestrial intelligence, though most scientists remain highly skeptical of such claims without more concrete evidence. The Fermi paradox might also be resolved by the idea that life tends to evolve in sync across the galaxy, triggered by similar cosmic conditions. In this scenario, we might be among the first wave of intelligent species, all emerging within a few million years of each other, all asking the same question: where is everybody? As our search continues, projects like the Search for Extraterrestrial Intelligence, or SETI, scan the skies for artificial signals. The Breakthrough Listen initiative, launched in 2015, represents the most comprehensive search for artificial radio and optical signals ever undertaken, targeting the million closest stars and the 100 closest galaxies. New telescopes like the James Webb Space Telescope analyze the atmospheres of planets orbiting other stars, looking for chemical signatures that might indicate the presence of life. While these efforts have not yet found evidence of extraterrestrial intelligence, each observation narrows the possibilities and refines our search strategies. Perhaps the most profound aspect of the Fermi paradox is what it suggests about our own future. If technological civilizations typically survive for millions of years, expanding throughout their galaxies, then our longevity prospects as a species might be quite good. But if civilizations tend to destroy themselves shortly after developing advanced technology, we may be approaching a crucial test of our wisdom and foresight. As you float in this space between wakefulness and dreams, consider the possibility that at this very moment, on a planet orbiting a distant star, another consciousness might be wondering about the same questions. Perhaps they too gaze at the night sky, pondering the strange silence of a universe that seems so hospitable to life, yet offers no clear evidence of it. The Great Silence remains one of the most thought-provoking mysteries in astronomy. Unlike the mystery of dark matter or dark energy, this puzzle touches directly on our place in the cosmos, on the question of whether the light of consciousness has illuminated other worlds, or whether we carry a uniquely precious flame in an otherwise dark universe. As we drift from this mystery toward our next cosmic enigma, remember that the very fact that we can ask these questions represents something remarkable. In a universe of mostly hydrogen and helium, on a small rocky planet orbiting an ordinary star, matter has organized itself into a form that can contemplate its own existence and the possibility of other minds among the stars. Whatever the answer to Fermi's question might be, the question itself speaks to something wondrous about our place in the cosmos. As you continue to drift peacefully through the mysteries of our cosmos, we approach perhaps the most profound question of all: what happened before the beginning? What existed before the Big Bang gave birth to space, time, and everything we know? This question takes us to the very edge of human understanding, to a realm where physics meets philosophy, where mathematics touches metaphysics. It is a question that challenges not only our scientific knowledge, but our very conception of what questions can be meaningfully asked. The Big Bang Theory, first proposed by Belgian priest and physicist Georges Lemaitre in 1927, describes how our universe began as an incredibly hot, dense point approximately 13.8 billion years ago. From this singular beginning, space itself began expanding, carrying with it the matter and energy that would eventually form galaxies, stars, planets, and ultimately, life capable of contemplating its own origins. Evidence for the Big Bang is abundant and compelling. We observe that galaxies are moving away from each other, suggesting the universe is expanding. The cosmic microwave background radiation, discovered in 1965, provides a snapshot of the universe when it was just 380,000 years old, confirming many predictions of Big Bang cosmology. The abundance of light elements like hydrogen, helium, and lithium matches what we would expect from the nuclear reactions in the first 3 minutes after the Big Bang. But the Big Bang theory describes the evolution of the universe from its earliest moments, not the moment of creation itself, and certainly not what came before. As we approach the beginning, our physics begins to break down. At extremely high energies and densities, our current theories become inadequate. General relativity, which describes gravity as the curvature of space-time, and quantum mechanics, which governs the behavior of particles, have not yet been successfully unified into a complete theory of quantum gravity. This theoretical limitation creates a cosmic horizon before which we cannot directly observe or conclusively theorize. Yet human curiosity compels us to ask, what preceded this beginning? Was there a before? Several fascinating possibilities have been proposed by cosmologists and theoretical physicists. Let us explore some of these ideas as you continue to relax and let your mind wander through these cosmic mysteries. One intriguing possibility is that there was no before, at least not in any meaningful sense we can comprehend. According to some interpretations of general relativity, time itself began with the Big Bang. Asking what came before would be like asking what is north of the North Pole. The question contains a hidden assumption that is not valid, the assumption that the concept of before can be extended infinitely backward. Stephen Hawking compared this to asking what lies south of the South Pole. Just as the surface of the Earth has a southernmost point beyond which the concept of south loses meaning, perhaps time has a beginning point beyond which the concept of before loses meaning. In Hawking's model, time near the Big Bang resembles space, with no singularity or boundary. Time simply curves back on itself, like the surface of the Earth, but with one fewer dimension. But many cosmologists find this answer unsatisfying. Various theories have been proposed that describe possible pre-Big Bang scenarios. One of the most prominent is the idea of an eternally inflating multiverse. According to inflationary theory, developed by physicists Alan Guth, Andre Linde, and others in the 1980s, the early universe underwent a period of exponentially rapid expansion called cosmic inflation, before settling into the more gradual expansion we observe today. Some versions of inflationary theory suggest this process continues eternally in different regions of space. In this eternal inflation scenario, our Big Bang was just one event in an infinite multiverse where new universes are constantly budding off from expanding space. Each universe might have different physical laws, different constants, different numbers of dimensions. Our universe would be just one bubble in an endless cosmic foam, with new bubbles forming continuously across an ever-expanding meta-universe. Another fascinating possibility is the cyclic or oscillating universe model. Perhaps our universe undergoes endless cycles of Big Bangs, followed by big crunches, where expansion eventually reverses into contraction, leading to another singularity and another Big Bang. In the most recent versions of this theory, proposed by physicists Paul Steinhardt and Neil Turok, our universe repeatedly collides with a parallel universe in a higher dimensional space, with each collision creating a new Big Bang. String theory, which attempts to unify all the forces of nature by modeling fundamental particles as tiny vibrating strings, suggests our universe might exist as a three-dimensional membrane, or brain, floating in a higher dimensional space. Our Big Bang might have resulted from a collision between our brain and another, releasing enormous energy that initiated the expansion of our universe. The quantum universe theory, drawing on principles of quantum mechanics, suggests that our universe might have emerged from a quantum fluctuation in a pre-existing state, sometimes called a quantum vacuum or a quantum foam. In this scenario, universes might naturally arise from quantum processes, popping into existence like virtual particles briefly appear in empty space, according to principles of quantum field theory. Perhaps one of the most mind-bending possibilities comes from the realm of mathematical physics. Our universe might be one solution among many to the fundamental equations that govern reality. Physicist Max Tegmark has proposed that the ultimate nature of reality is purely mathematical, and that any mathematically consistent structure exists as a universe somewhere in what he calls the mathematical universe hypothesis. Roger Penrose, a mathematician and physicist who shared the 2020 Nobel Prize in Physics, has proposed a model called conformal cyclic cosmology. In this view, the far future of one universe, when all matter has decayed and black holes have evaporated, becomes mathematically identical to the Big Bang of another universe. Time extends infinitely in both directions, with each aeon giving birth to the next. Some cosmologists even speculate that our universe might have emerged from a black hole in another, parent universe. The physics of black holes and the Big Bang share striking similarities, both involving extreme density and the warping of space-time. Theoretical physicist Lee Smolin has proposed a form of cosmic natural selection, where universes that produce many black holes have more offspring universes, leading to an evolutionary process that might favor universes capable of supporting complex structures like life. While these theories are fascinating, it is important to note that they remain speculative. Unlike many questions in science, the nature of what preceded the Big Bang might be fundamentally untestable, at least with current methods. We cannot directly observe what came before the cosmic microwave background radiation, which emerged when the universe was already 380,000 years old. Yet indirect evidence may eventually help us distinguish between these possibilities. Subtle patterns in the cosmic microwave background might reveal signatures of events from the earliest moments of the Big Bang or even before. Gravitational waves, ripples in space-time detected for the first time in 2015, might someday allow us to probe the first fractions of a second after the Big Bang, offering clues about what preceded it. Advanced mathematical models and computer simulations help scientists explore the logical implications of different pre-Big Bang scenarios. Theoretical work on quantum gravity, particularly string theory and loop quantum gravity, continues to develop frameworks that might explain the origin of our universe. As you continue to relax, imagine the vastness of possibility. Perhaps our universe has always existed in some form, cycling through endless transformations. Perhaps it emerged from something utterly unlike anything we can conceive. Perhaps the very concepts of time and causality that make us ask what came before are themselves products of the Big Bang, not applicable to what preceded it. The question of what happened before the Big Bang reminds us of the limits of human knowledge and the boundless nature of human curiosity. It humbles us with the realization that despite all our scientific progress, we may be like children on the shore of a vast ocean, collecting pretty shells while the great deep remains largely unexplored. Yet this humility does not diminish the wonder of our cosmic quest. The fact that we can even conceive of these questions, that we can develop mathematical models to explore them, that we can design experiments and observations to test our ideas, speaks to something remarkable about consciousness itself. We are the universe becoming aware of itself, matter contemplating its own origins. In the darkness behind your closed eyes, as you drift towards sleep, consider that the atoms in your body were forged in the hearts of ancient stars. The carbon, nitrogen, and oxygen that form your tissues were created by nuclear fusion billions of years ago. The hydrogen in the water of your cells dates back to the Big Bang itself. You are, in a very real sense, the universe exploring its own beginning. Our next cosmic mystery awaits, a peculiar anomaly in the oldest light we can observe, a cold spot in the cosmic microwave background radiation that defies simple explanation. But for now, rest in the profound question of beginnings, in the mystery that lies at the edge of time itself, where physics meets the unknowable and human imagination takes flight. What happened before the beginning? Perhaps the answer, if it exists at all, would transform our understanding not just of the cosmos, but of the nature of reality itself. As you continue to drift peacefully through the cosmic mysteries that surround us, we turn our attention to a peculiar anomaly in the oldest light we can observe, the cold spot in the cosmic microwave background radiation. This unexplained feature challenges our understanding of the early universe and hints at exotic possibilities that stretch the imagination. The cosmic microwave background radiation, or CMB, is the faint afterglow of the Big Bang, the oldest light in our universe. It fills all of space, arriving at Earth from all directions, a whisper from the cosmic dawn when our universe was just 380,000 years old. Before this time, the universe was an opaque plasma of charged particles. As it cooled, electrons combined with protons to form neutral hydrogen atoms, allowing light to travel freely for the first time. This ancient light has been traveling through space for 13.8 billion years. During this immense journey, the expansion of the universe has stretched its wavelength from visible light to microwave radiation, cooling it to just 2.7 degrees above absolute zero. When we observe the CMB, we are looking at a baby picture of our cosmos, a snapshot of the universe in its infancy. In 1965, Arno Penzias and Robert Wilson accidentally discovered this cosmic background radiation while working with a sensitive radio antenna at Bell Laboratories. They detected a persistent noise that came from all directions in the sky, which they initially thought might be caused by pigeon droppings on their equipment. After cleaning the antenna and eliminating other possible sources of interference, they realized they had stumbled upon something profound, the echo of the Big Bang itself. This discovery earned them the Nobel Prize in Physics and provided crucial evidence supporting the Big Bang theory. Decades later, satellite missions like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, revealing tiny temperature fluctuations of just 1 part in 100,000. These almost imperceptible ripples represent regions of slightly different density in the early universe, the seeds from which all cosmic structure would eventually grow. Galaxies, stars, planets, and ultimately life itself emerged from these subtle variations in the cosmic microwave background. But among these tiny fluctuations, scientists discovered something unexpected, a region in the constellation Eridanus, where the CMB is significantly colder than average. This anomaly, approximately 3.5 billion light-years across, has been named the cold spot. It appears to be about 70 millionths of a degree colder than its surroundings, a small difference in absolute terms, but statistically significant when compared to the otherwise remarkably uniform CMB. The cold spot was first detected by the WMAP satellite in 2004 and later confirmed by the more sensitive Planck satellite. Its existence poses a puzzle for cosmologists. According to the standard model of cosmology, temperature fluctuations in the CMB should follow what mathematicians call a Gaussian distribution, a bell curve of random variations. The cold spot appears to be too extreme, too unlikely to have occurred by chance in a perfectly random distribution. As you relax and imagine this vast, cold region in the primordial light of our universe, let us explore the various theories scientists have proposed to explain this cosmic anomaly. Perhaps the simplest explanation is that the cold spot is just a statistical fluke, an unlikely but possible random fluctuation. In a universe as vast as ours, even extremely improbable events will occur somewhere. Some cosmologists suggest that if we could observe enough of the universe, we might find other similar cold or hot spots. The cold spot might simply be the most extreme example within our observable universe, not truly anomalous, but just at the tail end of a normal distribution. But many researchers find this explanation unsatisfying, particularly because the cold spot appears alongside other large-scale anomalies in the CMB that also seem to defy the standard cosmological model. These include an alignment of features sometimes called the axis of evil and an overall lack of large-scale fluctuations. Together, these observations hint that something might be missing from our understanding of cosmic evolution. A more exotic possibility is that the cold spot represents the imprint of a collision between our universe and another universe in a vast multiverse. According to some versions of eternal inflation theory, our universe is just one bubble in an expanding meta-universe where new bubble universes are constantly forming. If another bubble universe collided with ours in the distant past, it might have left a detectable bruise on our CMB, appearing as an unusually cold or hot region. The implications of such a scenario would be profound. It would provide observational evidence for the existence of other universes, entities that many physicists have theorized but which have remained beyond our ability to detect. The cold spot might be the first empirical window into the multiverse, a glimpse of the cosmic context in which our universe exists. Another intriguing explanation involves what astronomers call a supervoid, an enormous region of space containing far fewer galaxies than average. In 2015, astronomers using the Pan-STARRS telescope in Hawaii and the Dark Energy Survey camera in Chile found evidence of such a void aligned with the cold spot. This supervoid, stretching some 1.8 billion light-years across, represents one of the largest known structures in the universe. As CMB photons pass through such a void, they lose energy climbing out of the gravitational well created by the absence of matter, causing a slight cooling effect. This phenomenon, known as the integrated Sachs-Wolf effect, might explain the temperature drop observed in the cold spot. However, follow-up studies have questioned whether this supervoid is large enough or empty enough to account for the full magnitude of the cold spot anomaly. Some theorists propose even more radical explanations. Perhaps the cold spot represents a topological defect in space-time itself, a cosmic texture left over from phase transitions in the early universe, similar to how cracks form in ice as water freezes. Such defects are predicted by certain unified theories of physics but have never been definitively observed. Still others suggest the cold spot might be evidence of exotic physics beyond the standard model of cosmology. Perhaps it indicates a region where dark energy, the mysterious force accelerating the expansion of the universe, behaves differently. Or it might represent a domain wall, a boundary between regions of the universe with different physical properties or constants. Some researchers have even speculated that the cold spot could be evidence of cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during the early universe. These extremely thin, extremely massive objects would create distinctive patterns in the CMB that might appear as unusual cold or hot regions. As you continue to relax, imagine the vastness of this cosmic anomaly. 3.5 billion light-years across. It dwarfs galaxy superclusters, the largest known structures in the universe. Light would take 3.5 billion years to cross it, a journey spanning a quarter of the age of the universe. Yet this enormous feature appears in radiation from the very birth of our cosmos, when the observable universe was just a fraction of its current size. The mystery of the cold spot reminds us how young our cosmic understanding truly is. Just a century ago, we did not know there were galaxies beyond our own. Just over 50 years ago, we had not yet detected the cosmic microwave background. The cold spot anomaly was discovered less than 2 decades ago. What other cosmic surprises might await us as our observations become more precise, our theories more refined, our understanding more complete? Current and future observatories continue to study the cold spot and other CMB anomalies. The Simons Observatory, currently under construction in Chile's Atacama Desert, will map the cosmic microwave background with unprecedented precision. The proposed CMB Stage 4 experiment would be even more sensitive, potentially able to detect the imprint of gravitational waves from the first instance after the Big Bang. These observations might help distinguish between the various explanations for the cold spot. If it represents a collision with another universe, we might find subtle polarization patterns around its edges. If it is caused by a supervoid, more detailed galaxy surveys should reveal the full extent of this cosmic emptiness. If exotic physics is responsible, other predictions of these theories might find support in new observations. The cold spot also challenges us to consider the limits of cosmology as a science. Unlike laboratory physics, where experiments can be repeated under controlled conditions, cosmologists have only one universe to observe. We cannot perform multiple trials or change variables to see how the cosmos responds. We must make the most of the single data point we have, our observable universe with its particular history and features. This makes cosmological anomalies like the cold spot especially valuable. They represent potential cracks in our current understanding, places where nature might be offering hints about deeper truths. Throughout the history of science, unexplained observations have often led to revolutionary discoveries. The slight discrepancy in Mercury's orbit led to Einstein's theory of general relativity. Unexpected patterns in the spectra of elements led to quantum mechanics. What new physics might the cold spot be pointing toward? As you drift deeper into relaxation, consider how the cold spot connects to the other cosmic mysteries we have explored. Like dark matter and dark energy, it reveals how much remains unknown about our universe. Like the question of what preceded the Big Bang, it hints at a cosmic context beyond our current understanding. Like the Fermi paradox, it reminds us that appearances can be deceiving, that what seems uniform at first glance may contain surprising anomalies upon closer inspection. The cold spot teaches us patience in our cosmic explorations. It has remained unexplained for nearly 2 decades, despite the efforts of brilliant minds around the world. Some cosmic puzzles may take generations to solve, others may remain mysterious for centuries. As we continue to observe and theorize, to build more powerful telescopes and develop more sophisticated models, we slowly push back the boundaries of our ignorance, revealing a universe more complex and wonderful than we had imagined. Our next cosmic mystery awaits, a question about the very geometry of our universe and why it appears so precisely balanced between different possible fates. But for now, rest in the contemplation of this vast cold region, in the primordial light, this whisper from the cosmic dawn that might be telling us something profound about the nature of reality itself. As you continue to drift peacefully through cosmic mysteries, we turn our attention to a question about the very shape of the universe itself. When cosmologists speak of the universe being flat, they are not referring to a 2-dimensional plane like a sheet of paper, but to the geometry of space-time itself, the very fabric of our cosmic reality. The puzzling flatness of our universe represents one of the most profound fine-tuning problems in physics, a cosmic coincidence that has led to revolutionary theories about the birth and evolution of everything we know. To understand cosmic flatness, we must first explore what it means for space-time to have a shape or geometry. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. He revealed that gravity is not a force pulling between masses, as Newton had described, but rather the curvature of space-time caused by matter and energy. Massive objects like stars and planets create dimples in the fabric of space-time, and other objects follow these curves, which we experience as gravitational attraction. This insight means that space-time itself can have different geometries depending on the amount and distribution of matter and energy it contains. Cosmologists consider three possible geometries for our universe at the largest scales: closed, open, or flat. A closed universe has positive curvature, like the surface of a sphere. In such a universe, parallel lines eventually converge. The angles in a triangle sum to more than 180 degrees, and if you travel far enough in one direction, you would eventually return to your starting point. A closed universe contains enough matter to eventually halt its expansion and collapse back on itself in a big crunch. An open universe has negative curvature, like the surface of a saddle or a potato chip. In this geometry, parallel lines diverge, the angles in a triangle sum to less than 180 degrees, and the universe expands forever at an accelerating rate. An open universe does not contain enough matter to halt its expansion. A flat universe exists precisely at the boundary between open and closed. It follows Euclidean geometry, where parallel lines remain parallel forever, the angles in a triangle sum to exactly 180 degrees, and the universe expands forever but at an ever-decreasing rate, at least in the absence of dark energy. The remarkable thing about our universe is that, according to our most precise measurements, it appears to be almost perfectly flat. Observations of the cosmic microwave background radiation by satellites like WMAP and Planck have measured the curvature of our universe to be indistinguishable from perfect flatness, with a margin of error less than 0.4%. This observed flatness presents a cosmic puzzle. The density of matter and energy in the universe that would produce perfect flatness is called the critical density. If the actual density differed from this critical value by even a tiny amount in the early universe, the difference would have been amplified over billions of years of cosmic evolution, resulting in a universe that is either obviously closed or obviously open today. The fact that we observe near perfect flatness billions of years after the Big Bang implies that the early universe must have been even more precisely flat, to a degree that seems impossibly finely tuned. Imagine balancing a pencil perfectly on its tip for 13.8 billion years. The initial conditions would need to be specified with extraordinary precision for such balance to persist. Similarly, the early universe would need to have had a density within 1 part in 100 trillion of the critical value to produce the flatness we observe today. As you continue to relax, let us explore the leading explanations for this cosmic coincidence, this remarkable flatness of our universe. The most widely accepted answer comes from a theory called cosmic inflation, proposed by physicist Alan Guth in 1979, and further developed by André Linde, Paul Steinhardt, and others in the early 1980s. According to inflation theory, the universe underwent a period of exponentially rapid expansion during the first fraction of a second after the Big Bang, increasing in size by a factor of at least 10 raised to the power of 26 in just 10 to the negative 33 seconds. This tremendous expansion would have stretched space flat regardless of its initial curvature, just as inflating a balloon smooths out its surface. A small patch of the balloon's surface appears increasingly flat as the balloon expands. Similarly, inflation would have stretched our observable universe from a tiny patch of the pre-inflationary cosmos, flattening any initial curvature to the remarkable degree we observe today. Inflation elegantly solves not only the flatness problem, but also other puzzles in cosmology. It explains why the universe appears so homogeneous and isotropic, why the cosmic microwave background radiation has nearly the same temperature in all directions, despite coming from regions that should never have been in causal contact without inflation. It also explains the origin of the slight density fluctuations that would eventually grow into the cosmic web of galaxies we observe today. Evidence for inflation comes from several sources. The cosmic microwave background shows patterns of temperature fluctuations that match predictions from inflationary theory. The distribution of galaxies across space also aligns with what we would expect if inflation occurred. While we cannot directly observe the inflationary epoch itself, its fingerprints appear throughout the observable universe. However, inflation is not without its critics and alternatives. Some physicists argue that inflation merely pushes the fine-tuning problem back a step rather than solving it. The conditions necessary for inflation to begin still require explanation, potentially their own form of fine-tuning. The theory also predicts a multiverse of bubble universes with potentially different physical laws, raising philosophical questions about its testability. Alternative explanations for cosmic flatness include varying speed of light theories, where the fundamental constants of nature may have been different in the early universe. Others propose bounce cosmologies, where our universe emerged from the collapse of a previous universe, with the bounce naturally producing a flat geometry. Some speculate that the anthropic principle might explain cosmic flatness. In a multiverse with many different regions or separate universes, each with different properties, intelligent beings would only evolve in regions compatible with life. A flat universe may be necessary for the complex structures that eventually lead to life and consciousness. We observe a flat universe because only in such a universe could observers like us exist to make the observation. Regardless of the ultimate explanation, the observed flatness of our universe reveals something profound about cosmic evolution. It suggests that the initial conditions of our universe were set with extraordinary precision, or that some physical process like inflation naturally drove the universe toward flatness regardless of its initial state. The flatness problem connects to deeper questions in theoretical physics. String theory and loop quantum gravity, two approaches to unifying general relativity with quantum mechanics, offer different perspectives on the geometry of spacetime at the most fundamental level. Some versions of string theory naturally predict a flat universe, while loop quantum gravity suggests that spacetime itself emerges from more fundamental quantum structures. Ongoing observations continue to refine our understanding of cosmic geometry. The Dark Energy Survey maps the distribution of billions of galaxies, revealing how dark matter and dark energy have shaped the large-scale structure of the universe. The Euclid Space Telescope, launched by the European Space Agency, studies how the geometry of the universe has evolved over cosmic history. Future experiments may detect primordial gravitational waves, ripples in spacetime created during the inflationary epoch. Such a discovery would provide strong support for inflation theory and help explain the remarkable flatness of our universe. The Simons Observatory and CMB Stage 4 experiments are specifically designed to search for these faint signals from the universe's first moments. As you drift deeper into relaxation, consider the vast implications of cosmic flatness. Our universe balances on a knife edge between eternal expansion and eventual collapse. Had the initial density been slightly higher, the universe would have recollapsed long ago, with no time for stars, planets, or life to evolve. Had it been slightly lower, matter would have spread too thinly for galaxies to form. Our existence seems to depend on this precise cosmic geometry. The flatness problem also reminds us that appearances can be deceiving. To ancient humans, the Earth appeared flat. To astronomers before the 20th century, the universe seemed static and eternal. Now we know the Earth is spherical and the universe is expanding. Perhaps what appears to us as perfect flatness hides subtle curvature beyond our current ability to detect. The history of science teaches us that improved observations often reveal new complexities in what once seemed simple. This cosmic mystery invites us to consider the limits of our understanding. We observe the universe through a narrow window of space and time, using instruments bound by current technology and theories constrained by current mathematics. The apparent flatness of our universe may have explanations we have not yet imagined, requiring concepts beyond our present grasp. Yet the pursuit of this mystery has already transformed our understanding of cosmic history. Inflation theory, developed to explain cosmic flatness, has become a cornerstone of modern cosmology, providing a coherent account of how our vast and complex universe emerged from quantum fluctuations in the earliest moments after the Big Bang. As we contemplate the geometry of everything, remember that you are part of this vast, flat universe. The atoms in your body emerged from the same primordial plasma that filled the early cosmos. The carbon in your cells was forged in ancient stars. The geometry of spacetime that puzzles cosmologists is the same geometry that curves around the Earth, holding you gently in its gravitational embrace as you rest. Our next cosmic mystery awaits, a phenomenon of sudden bursts of radio energy from the distant universe that continues to puzzle astronomers. But for now, rest in the contemplation of this vast, nearly flat cosmos, a universe so precisely balanced that it could give rise to stars, planets, and ultimately, to consciousness capable of wondering about its own remarkable geometry. As you continue to drift peacefully through the cosmic mysteries that surround us, we turn our attention to one of astronomy's newest and most puzzling phenomena, fast radio bursts, or FRBs. Imagine a flash of radio energy so powerful it releases as much energy in a millisecond as the sun produces in days, yet so brief it would be missed with a blink of an eye. These cosmic flashes represent one of the most active frontiers in astronomy, a puzzle that continues to challenge our understanding of the universe's most energetic processes. Fast radio bursts were discovered entirely by accident. In 2007, astronomer Duncan Lorimer and his student David Narkovich were analyzing archival data from the Parkes Radio Telescope in Australia. While searching for pulsar signals, they noticed something unusual, a powerful burst of radio waves lasting just a few milliseconds. This signal, unlike anything seen before, appeared to come from far outside our galaxy. It became known as the Lorimer burst, the first recognized FRB. For several years after this discovery, astronomers wondered if this might be a one-time event or even an error in the telescope's data. But in 2013, 4 more bursts were discovered in the Parkes archives. Soon, other radio telescopes around the world began detecting these mysterious signals. Today, astronomers have catalogued hundreds of fast radio bursts, with new ones being discovered almost daily. What makes these bursts so puzzling? First, they are incredibly brief, typically lasting just a few milliseconds. Second, they are extraordinarily energetic. Despite their brevity, they can be detected from billions of light years away, meaning they must release enormous amounts of energy. Third, the radio waves from FRBs show a characteristic sweep in frequency called dispersion, with higher frequencies arriving slightly before lower frequencies. This dispersion tells us that the signals have traveled through ionized gas, confirming their distant extragalactic origins. Perhaps most intriguingly, fast radio bursts come in 2 varieties. Some are one-off events, never seen to repeat. Others, called repeaters, produce multiple bursts from the same location, though with no obvious pattern to their timing. This distinction has led astronomers to wonder whether different types of cosmic phenomena might produce these similar but distinct signals. As you relax and let your mind wander through these cosmic mysteries, let us explore the various theories that have been proposed to explain the origin of fast radio bursts. One leading explanation involves magnetars, a special type of neutron star with an extraordinarily powerful magnetic field. Neutron stars themselves are already extreme objects, the collapsed cores of massive stars that have exploded as supernovae. Typically about 12 miles in diameter, but with a mass greater than our Sun, neutron stars represent matter in one of its most extreme forms, so dense that a teaspoonful would weigh billions of tons. Magnetars take this extremity further. Their magnetic fields are the strongest known in the universe, 1 trillion times stronger than Earth's magnetic field, and 1,000 times stronger than those of typical neutron stars. These fields are so intense, they actually affect the structure of atoms within their influence. Occasionally, magnetars experience starquakes, sudden adjustments in their structure that release tremendous energy. These events, or perhaps magnetic reconnection events in the magnetar's atmosphere, might produce the brief, powerful radio bursts we observe as FRBs. Support for this theory came in April 2020, when astronomers detected a fast radio burst coming from within our own Milky Way galaxy. Its source was a known magnetar called SGR 1935+2154. While this burst was much less energetic than typical extragalactic FRBs, its association with a magnetar provided the first direct evidence connecting these extreme stars to the FRB phenomenon. However, magnetars may not explain all fast radio bursts, particularly those that repeat. Some astronomers suggest that repeating FRBs might be produced by young neutron stars that are not necessarily magnetars. These young, rapidly spinning neutron stars might generate radio bursts through mechanisms similar to those that produce pulsar emissions, but far more energetic due to their youth and environmental conditions. Another possibility involves binary neutron star systems, where 2 neutron stars orbit each other closely. As they spiral together, their interaction might produce periodic bursts of radio energy. Eventually, such systems would merge in cataclysmic events that produce gravitational waves, similar to those first detected by LIGO in 2015. Some more exotic theories propose that at least some FRBs might be produced by cosmic strings, hypothetical, one-dimensional defects in space-time left over from the early universe. If cosmic strings exist, their vibrations or intersections could potentially release bursts of electromagnetic energy that might appear as FRBs. Black holes offer another possible explanation. Matter falling into a black hole forms an accretion disk, a swirling maelstrom of superheated gas. Instabilities in this disk, or in the jets that sometimes launch from the poles of black holes, might produce brief radio flashes. Alternatively, the collision and merger of black holes might generate FRBs through processes not yet fully understood. Perhaps the most speculative explanations involve advanced extraterrestrial civilizations. Some have suggested that powerful radio bursts could be produced by extraterrestrial technologies, perhaps as signals, as energy beams to propel spacecraft, or as byproducts of some unimaginable technology. While most astronomers consider natural explanations far more likely, the possibility, however remote, adds an intriguing dimension to the mystery. Whatever their cause, fast radio bursts have already proven valuable as cosmic tools. Because their radio waves are dispersed by the ionized gas they travel through, FRBs can be used to measure the density of this gas between galaxies, in what astronomers call the intergalactic medium. This helps map the distribution of matter in the universe, providing insights into cosmic structure formation. The hunt for fast radio bursts has driven the development of new radio telescopes and observing techniques. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, located in British Columbia, has been particularly successful at detecting FRBs. With its wide field of view and ability to monitor large portions of the sky continuously, CHIME discovers new bursts almost daily. Other dedicated FRB hunters include Australia's ASCAP, or Australian Square Kilometre Array Pathfinder, and China's FAST telescope, the world's largest single-dish radio telescope at 500 meters across. In the coming years, the Square Kilometre Array, a massive international radio telescope project being built in Australia and South Africa, will revolutionize FRB studies, potentially detecting thousands of bursts and pinpointing their locations with unprecedented precision. As astronomers locate more FRBs and trace them to their host galaxies, patterns are beginning to emerge. Many seem to come from the outskirts of galaxies, regions where magnetars and young neutron stars would be expected. Others appear associated with regions of active star formation, again consistent with young, massive stellar remnants as their sources. The mystery of fast radio bursts represents science in action, the process of discovery and investigation unfolding in real time. Unlike many cosmic phenomena that have been studied for centuries, FRBs were unknown just 15 years ago. Each new observation, each new burst detected, adds another piece to this cosmic puzzle. As you continue to relax, imagine these brief but powerful flashes occurring across the universe even now, momentary cosmic beacons signaling from distant galaxies. Each burst travels for billions of years across the expanding universe, carrying information about its source and about all the tenuous matter it encounters on its journey. When a fast radio burst finally reaches Earth, it might pass right through your body, its radio waves too weak after their long journey to be noticed without sensitive astronomical instruments. Yet these whispers from the distant cosmos tell tales of extreme physics, of matter and energy, in forms and conditions impossible to replicate in any laboratory on Earth. The study of fast radio bursts reminds us of how dynamic our understanding of the universe remains. Despite centuries of astronomical progress, the cosmos continues to surprise us with new phenomena, new mysteries that challenge our theories and expand our understanding. What seems inexplicable today may become textbook knowledge for future generations, just as quasars, pulsars, and gamma-ray bursts, once mysterious, are now understood as natural consequences of extreme astrophysical processes. It also demonstrates how technological advancement drives scientific discovery. The sophisticated radio telescopes and data processing systems that detect FRBs would have been impossible just decades ago. As our instruments become more sensitive, our computing more powerful, our methods more sophisticated, What other cosmic phenomena await discovery? What other mysterious signals might we detect from the depths of space? Whether fast radio bursts ultimately prove to be the work of magnetars, the death spirals of neutron stars, the vibrations of cosmic strings, or something not yet imagined, their study enriches our understanding of the universe in its most extreme manifestations. They remind us that the cosmos remains full of wonders and mysteries, that our journey of discovery continues with each unexpected flash from the depths of space. Our next cosmic mystery awaits, a question that touches on the very fabric of our reality and experience, the nature of time itself, why it flows in only one direction, and whether this most fundamental aspect of our existence may be an illusion or an emergent property rather than a fundamental feature of the universe. But for now, rest in the contemplation of these brief, brilliant cosmic flashes, these fast radio bursts that speak of extreme physics in distant galaxies. As you continue to drift peacefully through cosmic mysteries, we approach perhaps the most intimate yet elusive aspect of our reality, time itself. Time surrounds us, shapes our lives, flows through our experiences, yet when we try to grasp its fundamental nature, it slips through our fingers like cosmic smoke. The true nature of time represents one of the deepest mysteries in physics, a puzzle that touches not just our understanding of the universe, but our very experience of existence. We all intuitively understand time as the progression from past to future, the medium through which change occurs. We feel time's passage, remember the past, anticipate the future. Time seems to flow like a river, carrying us inevitably forward. Yet when physicists examine time at its most fundamental level, this intuitive picture begins to dissolve into profound questions that remain unanswered even after centuries of scientific inquiry. Perhaps the most striking feature of time is its apparent directionality. Unlike space, which allows free movement in any direction, time seems to flow in only one direction, from past to future. We remember the past but not the future. We can affect the future but not the past. Eggs break but do not unbreak. Coffee cools but does not spontaneously heat up. Entropy, the measure of disorder in physical systems, increases over time. This one-way flow gives time what physicists call an arrow, a preferred direction. Yet remarkably, the fundamental laws of physics do not share this directionality. The basic equations that govern particle interactions work equally well forward or backward in time. If you watched a film of two billiard balls colliding and then reversing the film, you could not tell which version ran forward and which backward. At the most fundamental level, physical laws exhibit time symmetry, making no distinction between past and future. This profound disconnect between time-reversible fundamental laws and our irreversible experience has puzzled physicists since the 19th century, when Ludwig Boltzmann first connected the arrow of time to entropy. According to Boltzmann, the arrow of time emerges from statistics and probability. There are simply many more ways for a system to be disordered than ordered, so natural processes tend toward disorder. A broken egg has many more possible arrangements of its matter than an intact egg. Time's arrow, in this view, is not fundamental but emergent from statistical behavior of countless particles. As you relax and contemplate this cosmic puzzle, consider an even more radical question that has troubled philosophers and physicists alike. Does time flow at all? Our subjective experience strongly suggests it does. We feel time passing, moments slipping from future to present to past. But Einstein's theories of relativity challenged this intuitive picture. According to relativity, time is not universal, but relative. Clocks run at different rates, depending on their velocity and the gravitational field they experience. Two observers in different reference frames will disagree about whether two events are simultaneous. An observer traveling near the speed of light experiences time dilation, where time passes more slowly compared to a stationary observer. These relativistic effects have been confirmed countless times in experiments. GPS satellites must account for time dilation to maintain their accuracy. Atomic clocks flown around the world show the predicted differences from identical clocks that remain stationary. Time, it seems, is more elastic and less absolute than our intuition suggests. Some theorists have proposed that rather than flowing like a river, time might better be thought of as a dimension, similar to the three dimensions of space. In this view, sometimes called block universe theory, all of time, past, present, and future exists at once. Our subjective experience of the present moment moving from past to future might be just that, a subjective experience, rather than a fundamental feature of reality. The physicist Julian Barber goes even further, suggesting that time might not exist fundamentally at all. In his view, what we perceive as time passing is actually a sequence of timeless arrangements of matter, like frames in a film. Each arrangement, or configuration, of the universe exists independently, with no actual flow between them. Our memories and the apparent causal connections between events create the illusion of time's passage. Quantum mechanics adds another layer of complexity to our understanding of time. The famous double-slit experiment shows that quantum particles seem to know the future, adjusting their behavior based on measurements that have not yet been made. Quantum entanglement allows for what Einstein called spooky action at a distance, where measurements on one particle instantaneously affect another, regardless of the distance separating them, seemingly transcending time itself. Some interpretations of quantum mechanics, like the Wheeler-DeWitt equation in quantum gravity, suggest that at the most fundamental level, the universe exists in a timeless state. Time might emerge only at larger scales, or through the process of quantum decoherence, where quantum systems interact with their environment to produce the classical world of our experience. The theoretical physicist Carlo Rovelli has proposed that time is fundamentally related to thermodynamics and information. In his view, the flow of time is the flow of information, the continuous creation of new correlations between physical systems. When you observe an event, new correlations form between your brain and the outside world. These correlations are irreversible, creating the appearance of time's arrow. Other researchers connect time's mysteries to consciousness itself. Perhaps our perception of time, the feeling of now moving from past to future, is a construction of our minds rather than a feature of external reality. Neuroscience reveals that our brains construct our experience of time in complex ways, often differing from physical time. During intense experiences, time seems to slow down. In boredom, it drags. In sleep, hours pass in what feels like moments. As we contemplate these mind-bending possibilities, it becomes clear that time may be both the most familiar aspect of our existence and the most mysterious. We live in time, feel its passage in every moment, yet its fundamental nature remains elusive, perhaps lying beyond our current physical theories or even our capacity to conceptualize. The quest to understand time drives much of modern theoretical physics. String theory attempts to unify quantum mechanics and general relativity, potentially revealing time's nature at the smallest scales. Loop quantum gravity suggests that space-time itself is quantized, composed of discrete units at the Planck scale, about 10 to the negative 35 meters. Causal set theory proposes that space-time is a vast collection of events with causal relationships between them, with time emerging from these causal connections. Experimental approaches to time's mysteries include precision measurements of time dilation and gravitational effects on time. The most accurate atomic clocks can now detect time differences caused by a change in height of just a few centimeters in Earth's gravitational field. Future experiments might test whether time is continuous or discrete at the smallest scales, whether quantum effects can reverse time's arrow, or whether consciousness plays a role in our experience of time's flow. Perhaps one of the most profound aspects of time's mystery is its connection to the beginning and end of our universe. If time began with the Big Bang, as most cosmologists believe, what does it mean to ask what came before? If time will eventually end, perhaps in a big rip, big crunch, or heat death of the universe, what does it mean for time itself to cease? Some speculative theories suggest that time might be cyclic, with our universe repeatedly expanding and contracting in an eternal sequence. Others propose that our universe is just one of many in a vast multiverse, each with its own version of time, perhaps even with different time dimensions, or time flowing at different rates. The mystery of time also connects to deep philosophical questions about determinism and free will. If the future already exists in a block universe, are our choices predetermined? If quantum mechanics introduces fundamental uncertainty into physical processes, does this create space for genuine choice? These questions have implications not just for physics, but for our understanding of ourselves as conscious beings making decisions in time. As you continue to relax and drift towards sleep, consider that the very mystery of time creates the context for rest and rejuvenation. Sleep itself represents a different state of temporal awareness, where dreams can compress or expand time, where hours pass in what subjectively feels like moments, or where brief seconds of dreaming can contain seemingly hours of experience. The puzzle of time reminds us that even the most familiar aspects of our reality can harbor profound mysteries. We have learned much about time's physical properties, its relativity, its connection to space, its relationship with entropy and information. Yet its deepest nature remains elusive, perhaps awaiting conceptual breakthroughs beyond our current theories, or perhaps representing a limit to what science can explain. As we leave this contemplation of time's mysteries, we move toward another cosmic puzzle, the apparent discrepancy in measurements of how quickly our universe is expanding. But for now, rest in the awareness of this moment, neither rushing toward the future nor clinging to the past, but simply being in the flowing river of time, carried gently toward dreams where time's constraints may temporarily dissolve. As you continue to drift peacefully through cosmic mysteries, we now turn to a puzzle that has emerged only in recent years, yet threatens to shake the foundations of modern cosmology. This is the mystery of the Hubble tension, a growing discrepancy in measurements of how quickly our universe is expanding. Like a cosmic detective story, this mystery involves conflicting evidence, competing methods, and potentially revolutionary implications for our understanding of the cosmos. The story begins in 1929, when astronomer Edwin Hubble made one of the most important discoveries in the history of astronomy. By measuring the distances to nearby galaxies and their velocities relative to Earth, Hubble found that more distant galaxies are moving away from us faster than closer ones. This relationship, now known as Hubble's law, revealed that the universe is expanding, a finding that would ultimately lead to the Big Bang theory. The rate of this expansion is described by a value called the Hubble constant, denoted by the letter h and subscript 0. It tells us how quickly space itself is stretching, usually expressed in kilometers per second per megaparsec. In simpler terms, it describes how fast 2 points in space are moving apart due solely to the expansion of the universe, with their separation increasing more rapidly the farther apart they already are. The Hubble constant is one of the most fundamental numbers in cosmology. It helps determine the age, size, and fate of our universe. It connects to the density of matter and energy, the geometry of space, and the mysterious dark energy that appears to be accelerating cosmic expansion. For decades, astronomers worked to measure this value with increasing precision, gradually narrowing down the possibilities. But in recent years, a troubling pattern has emerged. Different methods of measuring the Hubble constant have yielded consistently different results. This discrepancy, which has grown more significant as measurement techniques have improved, is what cosmologists call the Hubble tension. It represents one of the most significant unsolved problems in modern astronomy, with profound implications for our understanding of cosmic evolution. As you relax and contemplate this cosmic mystery, let us explore the conflicting measurements and what they might mean for our understanding of the universe. One approach to measuring the Hubble constant uses what astronomers call the cosmic distance ladder, a series of overlapping distance measurement techniques that extend from our cosmic neighborhood to the distant universe. This method relies on standard candles, objects whose intrinsic brightness is known, allowing their distance to be calculated by how dim they appear from Earth. The most important standard candles are Cepheid variable stars, whose pulsation periods relate directly to their luminosity, and Type Ia supernovae, exploding white dwarf stars that reach a consistent peak brightness. The most precise measurement using this cosmic distance ladder comes from the SH0ES project, led by Nobel laureate Adam Rees. Their latest results indicate a Hubble constant of about 73 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years of distance between 2 points in space, their separation increases by 73 kilometers every second due to cosmic expansion. The competing approach measures the Hubble constant in a completely different way, by studying the cosmic microwave background radiation, the afterglow of the Big Bang itself. This method uses observations from satellites like Planck to analyze tiny temperature fluctuations in this ancient light. Combined with our understanding of cosmic evolution based on the standard model of cosmology, These observations allow scientists to predict what the Hubble constant should be today. The Planck collaboration's analysis gives a Hubble constant of about 67.4 kilometers per second per megaparsec, significantly lower than the value found using the cosmic distance ladder. The difference of about 5.6 kilometers per second per megaparsec might seem small, but it far exceeds the stated uncertainties of both measurements. In scientific terms, the discrepancy now exceeds 5 sigma, the threshold physicists use to claim a definitive discovery. A third method, using gravitational waves from merging neutron stars as standard sirens, has begun providing independent measurements. Early results from this approach seem to fall between the other two values, but with larger uncertainties that make them compatible with both the higher and lower estimates. As you continue to relax, let us explore the possible explanations for this cosmic contradiction. What could cause different methods to yield persistently different results? The simplest explanation would be that one or both measurements contain unrecognized systematic errors. Perhaps something in the cosmic distance ladder method leads to underestimated distances, which would make the expansion rate appear faster than it truly is. Or maybe assumptions in the cosmic microwave background analysis introduce a bias toward lower values. Scientists have scrutinized both methods intensely, searching for such errors, but have not found any that could explain the full discrepancy. If systematic errors are not to blame, then perhaps our understanding of physics itself needs revision. The cosmic microwave background method relies on the standard model of cosmology, which includes assumptions about dark matter, dark energy, and how the universe evolved from its early state to the present. If this model is incomplete or incorrect in some way, its predictions for the Hubble constant could be off. Some theorists suggest that dark energy might be more complex than the simple cosmological constant used in the standard model. Perhaps dark energy has changed over time, growing stronger or weaker as the universe expanded. This would affect how the expansion rate has evolved since the early universe, potentially reconciling the different measurements. Others propose modifications to our understanding of gravity itself. Einstein's general relativity has passed every test so far, but perhaps at the largest cosmic scales, gravity behaves slightly differently than we expect. Such modifications could alter predictions about cosmic expansion in ways that might resolve the Hubble tension. More exotic possibilities include interactions between dark matter and dark energy, additional types of neutrinos beyond the 3 known varieties, or early dark energy that was significant shortly after the Big Bang, but has since faded away. Each of these would change how we interpret the cosmic microwave background data and could bring its implied Hubble constant closer to the directly measured value. Some researchers have even suggested that our local region of the universe might be unusual, residing in a large-scale underdensity, sometimes called a void. If we live in such a region, where matter is less concentrated than the cosmic average, the expansion rate we measure nearby would be higher than the global average probed by the cosmic microwave background. This would create exactly the kind of discrepancy we observe. As scientists work to resolve this mystery, new measurement techniques continue to be developed. The Gaia Space Observatory is mapping the positions and movements of over 1 billion stars in our galaxy with unprecedented precision, providing new ways to calibrate the cosmic distance ladder. The James Webb Space Telescope observes Cepheid variables and supernovae in distant galaxies with greater clarity than ever before, reducing uncertainties in direct measurements of the Hubble constant. Meanwhile, the Dark Energy Spectroscopic Instrument is creating a 3-dimensional map of the universe, tracking how its structure has evolved over time. This will provide another independent method to measure cosmic expansion. Similarly, future gravitational wave observatories will detect many more neutron star mergers, refining the standard siren approach. The Hubble tension reminds us that science often advances through contradictions and puzzles rather than smooth, continuous progress. Throughout history, discrepancies between theory and observation have pointed the way to revolutionary discoveries. The mismatch between Newtonian predictions and Mercury's orbit led to Einstein's general relativity. The ultraviolet catastrophe in black-body radiation helped launch quantum mechanics. Perhaps the Hubble tension will similarly lead to a breakthrough in our understanding of the cosmos. This puzzle also demonstrates the remarkable precision of modern cosmology. The fact that we can measure the expansion rate of the entire universe to within a few percent represents an extraordinary achievement, the culmination of decades of technological innovation and theoretical insight. The discrepancy exists only because our measurements have become so extraordinarily precise. As you drift deeper into relaxation, consider the vast cosmic drama represented by these competing measurements. The universe has been expanding for nearly 14 billion years, gradually spreading galaxies farther apart, diluting the cosmic density of matter and energy. This expansion, initially slowed by the gravitational attraction of matter, has more recently begun accelerating due to the influence of dark energy. The precise rate of this expansion connects to fundamental questions about cosmic history and fate. A faster expansion rate implies a younger universe, potentially creating tension with the ages of the oldest stars. It might also suggest a stronger dark energy, pointing toward an even more accelerated expansion in the future, perhaps eventually tearing apart galaxies, solar systems, and even atoms in a big rip. From our perspective on Earth, surrounded by the darkness of space, we can trace the expansion of the cosmos through careful observation and mathematical analysis. The light from distant galaxies, having traveled for billions of years across expanding space, carries encoded within it the history of cosmic expansion. By deciphering this light, we reconstruct the biography of our universe, chapter by chapter, from its earliest moments to the present day. The Hubble tension reminds us that this cosmic story remains unfinished, with mysteries still to solve and discoveries yet to make. As our instruments become more precise, our theories more refined, our understanding more complete, we continue to explore the vast, expanding cosmos that surrounds us, humbly acknowledging that nature often holds surprises beyond our current comprehension. Our next cosmic mystery awaits, an exploration of the true nature of black holes, those dark and enigmatic objects where space and time themselves seem to end. But for now, rest in the contemplation of our expanding universe, stretching ever outward from its fiery beginning, toward a fate still being written in the language of space, time, matter, and energy. As you continue to drift peacefully through the cosmic mysteries that surround us, we now approach perhaps the most enigmatic objects in our universe, black holes. These regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp, represent the limits of our understanding of physics. They are cosmic paradoxes, mathematical extremes made real, places where Einstein's relativity and quantum mechanics collide in ways we still do not fully comprehend. Let us explore the profound mysteries of black holes as you relax, and let your imagination journey to the edge of the known. The concept of an object so massive that light cannot escape dates back surprisingly far in scientific history. In 1783, English natural philosopher John Michell speculated about what he called dark stars, bodies so dense that their escape velocity would exceed the speed of light. Similar ideas were proposed independently by French mathematician Pierre-Simon Laplace in 1796. But these early concepts were based on Newtonian physics, which treats light as particles and gravity as a force acting at a distance. Our modern understanding of black holes emerged from Einstein's general theory of relativity, published in 1915. This revolutionary theory reconceived gravity not as a force, but as the curvature of space-time caused by mass and energy. Though Einstein himself was initially skeptical about their existence, his equations predicted that if matter becomes sufficiently concentrated, it would create a region from which nothing can escape, a singularity surrounded by an event horizon. The term black hole was coined much later by American physicist John Wheeler in 1967. As he described them, black holes represent where space-time has collapsed completely, creating a region of infinite density shrouded by a boundary beyond which no information can reach us. This boundary, the event horizon, marks the point of no return. Once anything crosses this threshold, be it matter, light, or information of any kind, it is forever lost to the outside universe, drawn inexorably toward the singularity at the center. For decades after Einstein's predictions, black holes remained theoretical curiosities. Many physicists, including Einstein himself, doubted they could form in reality. But gradually, evidence mounted. In 1964, astronomers discovered quasars, incredibly bright objects that outshine entire galaxies, yet emanate from regions no larger than our solar system. The only explanation for such concentrated energy is the superheated material, swirling around supermassive black holes at the centers of distant galaxies. Closer to home, astronomers found Cygnus X1, a strong source of X-rays that appeared to be a normal blue star orbiting an invisible companion. The invisible object's mass, calculated from its gravitational effects on the visible star, proved too great for a neutron star. It could only be a black hole, the collapsed core of a once massive star. Similar binary systems have since been discovered, providing strong indirect evidence for stellar mass black holes formed from the deaths of stars much more massive than our Sun. The most compelling evidence came in 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Using 8 radio telescopes around the world working together as a virtual Earth-sized telescope, they captured the silhouette of the supermassive black hole at the center of galaxy M87, a giant elliptical galaxy 55 million light-years from Earth. This black hole, with a mass of about 6.5 billion suns, appears as a bright ring of superheated gas surrounding a dark central region, the shadow cast by the event horizon itself. Even more direct evidence came in 2015, when the LIGO and Virgo collaborations detected gravitational waves, ripples in spacetime, produced by the merger of 2 black holes over 1 billion light-years away. Since then, dozens of black hole mergers have been detected through their gravitational wave signatures, confirming not only that black holes exist, but that they collide and merge, growing larger over cosmic time. At the center of our own Milky Way galaxy lurks a supermassive black hole called Sagittarius A star. Though invisible directly, its presence is revealed by the orbits of stars around a central point that contains 4 million solar masses within a space smaller than our solar system. Nothing but a black hole could be so massive yet so compact. In 2020, the Nobel Prize in Physics was awarded to researchers who provided conclusive evidence for this invisible cosmic giant at the heart of our galaxy. So we know black holes exist, but what is their true nature? What happens within that dark sphere defined by the event horizon? What occurs at the singularity, where our current theories predict density becomes infinite and space-time curvature reaches its mathematical limit? Here we enter the realm of deep mystery, where our best theories make contradictory predictions, and where perhaps entirely new physics awaits discovery. As you continue to relax and contemplate these cosmic enigmas, let us explore some of the profound puzzles posed by black holes. The first concerns information. According to quantum mechanics, information cannot be destroyed. The complete data about a physical system, down to the precise state of every particle, must be preserved even as the system evolves. Yet black holes seem to destroy information. Anything that falls into a black hole, be it a book, a spaceship, or a person, appears completely lost to the outside universe. All those distinct possibilities collapse to a single outcome, a slightly larger black hole characterized only by its mass, spin, and electric charge. This apparent destruction of information creates what physicists call the black hole information paradox. Proposed by Stephen Hawking in the 1970s, this paradox highlights the fundamental conflict between general relativity, which suggests information is irretrievably lost within a black hole, and quantum mechanics, which insists information must be preserved. Hawking's own work added another layer to this paradox. In 1974, he made the remarkable discovery that black holes aren't completely black. Due to quantum effects near the event horizon, black holes emit a faint form of radiation, now called Hawking radiation. This radiation causes black holes to slowly lose mass and energy, eventually evaporating completely over unimaginably long timescales. But this evaporation intensifies the information paradox. The Hawking radiation appears to be purely thermal, carrying no information about what fell into the black hole. So when the black hole finally disappears, where does all the information about everything that ever fell into it go? Is it truly lost, violating a fundamental principle of quantum mechanics? Or is it somehow encoded in the radiation, preserved in subtle correlations that are extraordinarily difficult to detect? Various solutions have been proposed. Perhaps information is stored in subtle correlations within the Hawking radiation, preserved in ways too complex for us to currently calculate. Or maybe information is recorded in a kind of hologram on the event horizon itself, never actually entering the black hole's interior. Some theorists suggest that information might be transferred to parallel universes through wormholes connected to the black hole's interior. Others propose that as a black hole approaches the end of its evaporation, it leaves behind a remnant that contains all the information of everything that ever fell into it. In recent years, progress has come from a concept called the holographic principle, which suggests that all the information contained within a volume of space can be encoded on its boundary. Applied to black holes, this leads to the idea that everything falling into a black hole leaves an imprint on its event horizon, like a three-dimensional image projected onto a two-dimensional surface. The information isn't lost, just transformed and preserved in a different form. As strange as these ideas may sound, they represent serious attempts by theoretical physicists to resolve one of the most profound contradictions in modern physics. The resolution of the information paradox may require a synthesis of general relativity and quantum mechanics, a theory of quantum gravity that has eluded physicists for decades. Another profound mystery concerns what happens at the singularity, the point at the center of a black hole where, according to general relativity, matter is crushed to infinite density and space-time curvature becomes infinite. Such infinities typically signal the breakdown of a physical theory, suggesting that general relativity alone cannot describe what truly happens there. Most physicists believe that some form of quantum gravity, perhaps string theory or loop quantum gravity, will eventually replace these singularities with more physically reasonable scenarios. Perhaps matter never reaches infinite density but transitions into some exotic quantum state we don't yet understand. Or maybe, as some versions of string theory suggest, black holes connect to white holes in other regions of space-time, or even other universes, forming wormholes or Einstein-Rosen bridges that might theoretically allow travel between distant regions of space. These speculations lead to another puzzling aspect of black holes, the firewall paradox. According to calculations by theoretical physicists, quantum effects near the event horizon might create a wall of intense energy, or firewall, that would incinerate anything falling into the black hole. This contradicts the principle of equivalence from general relativity, which suggests that someone falling into a black hole should notice nothing special when crossing the event horizon. The firewall paradox represents another conflict between quantum mechanics and general relativity, highlighting the need for a unified theory. Beyond these theoretical puzzles, black holes raise profound philosophical questions about the nature of space, time, and existence itself. If you could somehow survive the journey into a black hole, what would you experience? According to general relativity, as you approach the event horizon, time would appear to slow down relative to distant observers. From their perspective, you would appear to freeze at the event horizon, your image growing ever dimmer and redder due to gravitational redshift, never quite crossing over. But from your perspective, nothing special would happen at the horizon itself. You would cross it in finite time according to your own clock, continuing your journey toward the singularity. Once inside, the topology of space-time changes dramatically. All possible paths, regardless of direction, lead to the singularity. The radial dimension becomes time-like rather than space-like, meaning that motion toward the singularity becomes as inevitable as the forward flow of time in the outside universe. The singularity does not exist at a place, but at a time, in your future, unavoidable. What would you see as you fell deeper? The outside universe would appear compressed into a small, bright circle above you. As you approach the singularity, tidal forces would stretch you vertically and compress you horizontally, a process graphically called spaghettification. For a stellar mass black hole, these tidal forces would become lethal long before you reach the event horizon. But for a supermassive black hole like those at galactic centers, tidal forces at the event horizon are much milder, potentially allowing you to cross the horizon intact before being torn apart nearer the singularity. If black holes seem strange, rotating black holes, or Kerr black holes, are stranger still. Most black holes likely spin due to the conservation of angular momentum from their parent stars or from material falling into them. This rotation distorts space-time in peculiar ways, creating regions called ergospheres, where space itself is dragged along with the black hole's rotation. Even more exotic is the theoretical inner structure of rotating black holes, which might contain ring singularities rather than point singularities, and possibly gateways to other regions of space-time. The theoretical physicist Roy Kerr discovered the mathematical solution for rotating black holes in 1963. Unlike the simpler Schwarzschild black holes, which are perfectly spherical, Kerr black holes bulge at their equators due to their spin. Inside a rotating black hole, the mathematics suggests the existence of a region called the Cauchy horizon, beyond which determinism breaks down. Past this boundary, the future cannot be predicted even in principle from the present state of the universe, a profound challenge to our understanding of cause and effect. Some rotating black hole solutions even permit closed time-like curves, paths through space-time that return to their starting point in time as well as space, theoretically allowing time travel. Most physicists believe that in real black holes, instabilities would prevent such exotic structures from forming, preserving the principle of causality. But the mathematics tantalizes us with possibilities at the edge of comprehension. As if these puzzles weren't enough, black holes also raise questions about the limits of computation and the nature of consciousness. Physicist Seth Lloyd has proposed that black holes represent the ultimate computing devices, potentially capable of processing information at rates far exceeding any conventional computer. The holographic principle suggests that the maximum amount of information that can be contained in a region of space is proportional to the area of its boundary, a limit first proposed in the context of black hole thermodynamics. This connection between information, entropy, and black holes leads to speculations about whether physical reality itself might be fundamentally information theoretic, a vast computation playing out according to quantum algorithms. Black holes, in this view, represent not just extreme objects in physical space, but extreme cases in information theory, places where bits of information are compressed to their theoretical maximum density. The mystery of black holes extends beyond theoretical physics to observational astronomy. In recent years, astronomers have discovered black holes in mass ranges thought to be impossible, or at least highly improbable, according to standard stellar evolution models. These intermediate mass black holes, too massive to form from single star collapse, yet smaller than typical supermassive black holes, pose puzzles for theories of black hole formation and growth. At the other extreme, some galaxies harbor ultramassive black holes, behemoths exceeding 10 billion solar masses. How these cosmic monsters formed so early in cosmic history remains unknown. Did they grow from smaller seed black holes, rapidly accreting matter in the dense early universe? Did they form directly from the collapse of enormous gas clouds before stars could form? Or did they result from mergers of smaller black holes, building hierarchically like the galaxies themselves? The relationship between black holes and their host galaxies presents another intriguing puzzle. The mass of a galaxy's central black hole correlates strongly with properties of the galaxy's bulge, suggesting a co-evolution of black holes and galaxies. Yet the physical scales differ enormously, the black hole's direct gravitational influence extending only a tiny fraction of the galaxy's size. This correlation hints at feedback mechanisms through which black holes regulate galactic star formation, perhaps through enormous outflows of energy during their active quasar phases. Primordial black holes represent yet another mystery. Unlike black holes formed from collapsed stars or accumulated matter at galactic centers, primordial black holes would have formed in the extreme densities of the very early universe, minutes or seconds after the Big Bang. Such black holes could have masses ranging from microscopic to thousands of solar masses. While no primordial black holes have been definitively detected, they remain candidates for the mysterious dark matter that pervades the universe. At the smallest extreme, microscopic black holes might theoretically be created in particle accelerators like the Large Hadron Collider, though only in certain speculative models with extra dimensions of space. Such quantum black holes would evaporate almost instantly via Hawking radiation, potentially providing experimental evidence for both Hawking's predictions and theories of quantum gravity. Despite sensationalist headlines, such microscopic black holes pose no danger to Earth, as their gravitational influence would be negligible and their lifetimes shorter than a nanosecond. The study of black holes also intersects with one of the most profound questions in science, the origin of the universe itself. Some cosmological models suggest our universe began as something like the time reverse of a black hole collapse, an expansion from a singularity rather than a contraction toward one. Understanding the physics of black hole singularities might provide insights into the Big Bang singularity, potentially revealing whether our universe is one among many in a vast multiverse. In recent years, black holes have moved from theoretical curiosities to observational mainstays of astronomy. The Event Horizon Telescope continues its work, imaging the shadows of supermassive black holes with ever greater precision. The LIGO and Virgo gravitational wave observatories detect new black hole mergers regularly, building a census of black hole masses and spins throughout the universe. X-ray telescopes observe the superheated plasma in black hole accretion disks, revealing how material behaves in the extreme gravitational fields near event horizons. Future observatories promise even more revelations. The LISA mission, a space-based gravitational wave detector planned for the 2030s, will observe supermassive black hole mergers across cosmic history. The next generation of 30-meter class optical telescopes will track individual stars orbiting the Milky Way's central black hole with unprecedented precision, potentially testing general relativity in the strongest gravitational fields accessible to direct observation. As you continue to relax and drift towards sleep, consider the profound connections between black holes and our own existence. The elements that form your body, the carbon, nitrogen, and oxygen essential to life, were forged in the cores of massive stars, the same stars that leave behind black holes when they die. The supermassive black hole at our galaxy's center has helped shape the Milky Way's evolution, creating the conditions that ultimately allowed life to emerge on at least one small planet. We are, in a very real sense, connected to these cosmic extremes, these places where space and time reach their limits. The mystery of black holes reminds us of how far human understanding has progressed, and yet how much remains unknown. From theoretical predictions to observational confirmations, from mathematical abstractions to directly imaged shadows, black holes have moved from the realm of speculation to established science. Yet at their cores, quite literally, fundamental mysteries remain, puzzles that may require new physics, new mathematics, new ways of thinking about space, time, matter, and information. Perhaps most profoundly, black holes remind us of the limits of our current understanding. Like the medieval maps that marked unexplored territories with the phrase "here be dragons," the singularities of black holes mark the boundaries of known physics. Beyond these boundaries may lie revolutionary insights, connecting quantum mechanics and general relativity, unifying the four fundamental forces, perhaps revealing space and time themselves to be emergent rather than fundamental. As theoretical physicist John Wheeler once said, black holes teach us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but. In the deep mystery of black holes, we confront not just the limits of our theories, but the limits of our imagination, the edge of what we can conceive within the constraints of human minds, evolved on the surface of a small planet, orbiting an ordinary star. Yet despite these limits, we continue to probe and question, to observe and theorize, to push the boundaries of knowledge ever outward, even as we contemplate objects from which nothing can escape. In this cosmic quest, we find something quintessentially human, our unique capacity to wonder, to seek understanding even of the most extreme and inaccessible regions of our universe. Beyond the theoretical puzzles we've discussed, black holes have practical importance in modern astrophysics. They serve as cosmic laboratories for testing the most extreme predictions of general relativity. The intense gravitational fields around black holes create observable effects that would be imperceptible in weaker gravitational regimes. Light bending around black holes, the precession of orbiting stars, the dragging of space-time itself by rotating black hole Soul. These effects provide opportunities to test Einstein's equations under conditions impossible to replicate on Earth. Black holes also play crucial roles in the most energetic phenomena in the universe. Gamma-ray bursts, the brightest electromagnetic events known, are thought to result from either the collapse of massive stars into black holes or the merger of neutron stars potentially forming a black hole. These bursts release more energy in seconds than our sun will emit in its entire 10 billion-year lifetime, briefly outshining entire galaxies. Closer to home, microquasars within our own galaxy produce miniature versions of the jets seen in distant quasars. These stellar mass black holes, accreting matter from companion stars, create relativistic jets of particles that extend for light years, providing accessible examples of how matter behaves in extreme environments. Similarly, quiescent black holes in binary systems offer opportunities to study how stars interact with these invisible gravitational wells. The environments around supermassive black holes generate some of the most exotic forms of matter known to science. The accretion disks that feed these cosmic giants can reach temperatures of millions of degrees, creating a state known as quark-gluon plasma, where the fundamental constituents of protons and neutrons flow freely. This state of matter likely existed in the first microseconds after the Big Bang and is recreated fleetingly in particle accelerators, but exists persistently in the extreme environments around black holes. Perhaps one of the most intriguing aspects of black holes is their potential connection to wormholes, hypothetical tunnels through space-time that could connect distant regions of our universe or even link to other universes. Einstein's equations, specifically the Einstein-Rosen bridge solution discovered in 1935, suggest that black holes might form the entrance to such tunnels. While traversable wormholes remain firmly in the realm of theoretical speculation, their mathematical connection to black holes represents another layer of mystery surrounding these cosmic enigmas. The mathematics describing black holes has led to unexpected connections with other areas of physics through a concept called the ADS-CFT correspondence. This remarkable theoretical framework, proposed by Juan Maldacena in 1997, suggests that gravity in a space with a particular geometry is mathematically equivalent to a quantum field theory without gravity in a space with one fewer dimension. This correspondence has allowed physicists to translate intractable problems involving quantum gravity into more manageable problems in quantum field theory, providing insights into both black hole physics and quantum chromodynamics, the theory of the strong nuclear force. This connection between black holes and quantum field theory extends even further through the study of quantum entanglement. Recent theoretical work suggests that the geometry of space-time itself might emerge from quantum entanglement between fundamental constituents of reality. In this view, the event horizon of a black hole represents a boundary between regions with different patterns of quantum entanglement, and gravity emerges as a consequence of these entanglement structures. If correct, this perspective would represent a profound unification of quantum mechanics and general relativity, with black holes serving as the crucial conceptual bridge. The mystery of black holes extends to their role in the far future of our universe. In the extremely distant future, after all stars have burned out and all matter has either been accreted into black holes or dispersed into tenuous gas, black holes will dominate the cosmos. Over unimaginably long timescales, these black holes will slowly evaporate through Hawking radiation. A stellar mass black hole would take approximately 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. Supermassive black holes would persist even longer, up to 10 to the power of 100 years. In these remote epochs, black hole evaporation might provide the only source of energy and entropy production in an otherwise dead universe. This eventually leads to a consideration of the ultimate fate of information in our universe. If black holes are indeed the final repositories of ordered information in the far future cosmos, then their eventual evaporation represents the ultimate information processing event in cosmic history. The resolution of the black hole information paradox thus speaks not just to abstract theoretical concerns, but to the final disposition of all information, all complexity, all patterns that ever existed in our universe. Some philosophers and physicists have even speculated about the possibility of advanced civilizations using black holes as energy sources or computational resources in the far future. Theoretically, energy could be extracted from rotating black holes through a process called the Penrose process, where objects split apart in the ergosphere, with one piece falling into the black hole and the other escaping with more energy than the original object. Black holes might also serve as the ultimate data storage devices, potentially encoding vast amounts of information on their event horizons, according to the holographic principle. The connection between black holes and computation extends further into speculative realms. Some versions of a concept, called the black hole complementarity principle, suggest that information falling into a black hole might be both lost to the outside universe from one perspective and preserved in another, similar to how quantum objects can exist in superposition states until measured. This form of complementarity might have implications for quantum computation and information theory beyond black hole physics itself. Black holes might even play a role in the evolution of advanced intelligence. In the far future, as stars burn out and conventional energy sources dwindle, gaining access to the energy and information processing potential of black holes could become an evolutionary imperative for post-biological intelligence. If consciousness someday transitions to substrate-independent forms, these entities might cluster around black holes as the only remaining oases of free energy and computational capacity in an otherwise exhausted cosmos. On the grandest scale, the study of black holes connects to multiverse theories and the potential for existence beyond our observable cosmos. Some versions of inflationary cosmology suggest that black hole interiors might spawn new universes, with each singularity giving birth to a new expanding region disconnected from our own. If true, this would mean that black holes serve not just as endpoints within our universe, but as gateways to entirely new cosmological realms, each with its own physics, its own evolution, and potentially its own black holes, continuing the process of cosmic reproduction. This brings us to philosophical questions about knowledge and the limits of science. Black holes challenge our conception of what it means to know something scientifically. The event horizon represents not just a physical boundary, but an epistemological one, beyond which direct observation seems impossible in principle. Yet through mathematics, indirect observation, and theoretical inference, we have constructed detailed models of what happens beyond these horizons. This tension between the seemingly unknowable and our drive to know represents a profound philosophical aspect of black hole physics. For all our theoretical progress, we must acknowledge how young our understanding truly is. The confirmation that black holes actually exist came only in the past few decades. The first image of a black hole's shadow is less than 5 years old. The detection of gravitational waves from merging black holes occurred just 8 years ago. We are in the early days of black hole astronomy, with each new observation bringing surprises and challenges to our theories. Consider the discoveries still to come. The next generation of gravitational wave observatories will detect black hole mergers across cosmic history, building a comprehensive census of these objects. Advanced imaging techniques might reveal the detailed structure of accretion flows around event horizons, testing models of how matter behaves in extreme gravitational fields. Perhaps most exciting, the intersection of quantum information theory with black hole physics might lead to experimental tests of Hawking radiation or the holographic principle, bringing these theoretical concepts into the realm of observational science. The journey to understand black holes mirrors humanity's broader scientific quest. We begin with observations that challenge existing theories. We develop new mathematics to describe phenomena at the limits of our understanding. We build increasingly sophisticated instruments to test our theories against reality. And in this process, we occasionally glimpse deeper patterns, more fundamental principles that reshape our conception of reality itself. The mystery of black holes speaks to something profound about human curiosity and our place in the cosmos. We are a young species on a small planet orbiting an ordinary star, yet we dare to contemplate objects where space and time themselves break down, where the laws of physics reach their limits, where reality as we understand it is stretched beyond recognition. In this contemplation, we touch something transcendent, a connection to the deepest structures of existence itself. As you drift closer to sleep, imagine the silent darkness of a black hole, not as a place of fear but as a cosmic koan, a paradox that pushes the mind beyond conventional understanding. These cosmic enigmas, scattered throughout our universe like koans written in the language of gravity and light, invite us not just to know, but to wonder, not just to calculate, but to contemplate the profound mystery at the heart of existence. The poet Rainer Maria Rilke once advised that we should love the questions themselves, to live the questions now, rather than anxiously seeking immediate answers. Black holes embody this wisdom, offering questions that may take generations or centuries to answer, if they can be answered at all. Yet, in living with these questions, in allowing them to expand our conception of what is possible, we participate in one of humanity's noblest endeavors, the quest to understand our cosmic context. As we leave the mystery of black holes behind, our cosmic journey draws toward its conclusion. In our final contemplation, we will consider all these unsolved mysteries together, reflecting on what they tell us about the universe and our place within it. But for now, Let the darkness of black holes carry you deeper into relaxation, into the gentle void of restful sleep, where perhaps your dreaming mind might touch mysteries beyond the reach of waking thought. As our journey through the greatest unsolved cosmic mysteries draws to a close, we find ourselves not with a collection of answers, but with a treasury of questions. Questions that stretch from the smallest scales of quantum particles to the vast expanses of the multiverse. Questions that connect the earliest moments after the Big Bang to the unimaginably distant future of our expanding cosmos. Questions that may take generations, centuries, or even millennia to answer, if they can be answered at all. Let us take a moment, as you drift toward peaceful slumber, to reflect on what these mysteries tell us about the universe and our place within it. What does it mean that after centuries of astronomical progress, after sending spacecraft to the edge of our solar system and peering across billions of light years with our most powerful telescopes, we still cannot identify the nature of 95% of the contents of the cosmos? Dark matter and dark energy, these invisible presences that shape the largest structures in the universe and determine its ultimate fate, remain beyond our grasp. We have mapped their effects, tracked their influence on galaxies and the cosmic expansion, yet their fundamental nature eludes us. They remind us of how young our scientific understanding truly is, how much remains to be discovered about the most basic components of our reality. The great silence of the cosmos, the puzzling absence of signals from other technological civilizations, speaks to the precious rarity of conscious life, or perhaps to its fragility. Either we are remarkably unusual in a universe teeming with simple life, or technological civilizations typically face existential challenges that limit their longevity. Either possibility carries profound implications for our own future, for the choices that lie before us as we develop technologies of increasing power and reach. When we contemplate what came before the Big Bang, we touch the limits not just of our knowledge, but potentially of knowledge itself. We encounter questions that may lie beyond the realm of empirical science, where physics merges with philosophy and mathematics touches metaphysics. These boundary questions remind us that science is not a collection of final answers, but a method, a way of engaging with mystery that acknowledges its own limitations while continuously pushing beyond them. The cold spot in the cosmic microwave background, the puzzling flatness of our universe, the strange behavior of fast radio bursts. All these anomalies and cosmic coincidences hint at how incomplete our current models remain. They are the loose threads in the cosmic tapestry, the places where reality seems to defy our expectations. Throughout history, such anomalies have often led to revolutionary discoveries, to paradigm shifts that transform our understanding of nature. What revolutions await in the resolution of these cosmic puzzles? The nature of time itself, flowing inexorably from past to future in our experience yet showing no preferred direction in our most fundamental equations, connects physics to consciousness in ways we are only beginning to explore. It reminds us that we are not just observers of the cosmos, but participants in it, that our experience of reality is shaped by the very structure of our minds that evolved on a small rocky planet orbiting an ordinary star in the suburbs of an average galaxy. The Hubble tension, that growing discrepancy in measurements of the cosmic expansion rate, demonstrates science in action, the process by which conflicting observations drive theoretical advances. It reminds us that precision matters, that as our measurements become more exact, new mysteries emerge in the decimal places, in the small discrepancies that signal incompleteness in our models. And black holes, those cosmic paradoxes, where space and time as we understand them cease to exist, where general relativity and quantum mechanics collide in ways we cannot yet reconcile, represent the frontiers of fundamental physics. They are nature's laboratories for testing theories of everything, cosmic anvils upon which we forge our deepest understanding of reality itself. What unites all these mysteries is their ability to humble us, to remind us of how vast the universe is and how limited our perception remains. Yet paradoxically, they also speak to something remarkable about human consciousness, about our capacity to ask questions that stretch beyond our immediate surroundings, beyond our direct experience, beyond the world that evolution prepared us to understand. Consider the extraordinary journey of human understanding. Our ancestors gazed at the night sky with naked eyes, creating myths and stories to explain what they saw. The invention of the telescope allowed Galileo to discover the moons of Jupiter and the phases of Venus, revelations that helped overturn a geocentric model of the universe that had persisted for millennia. The spectroscope revealed the chemical composition of distant stars, showing that the same elements found on Earth exist throughout the cosmos. Radio telescopes detected the cosmic microwave background, confirming the Big Bang and transforming cosmology from speculation to precision science. Each technological advance has revealed new mysteries along with new knowledge. With every expansion of our observational reach, the universe has appeared larger, older, stranger, and more wonderful than previously imagined. There is no reason to think this pattern has ended. Our current puzzles, the cosmic mysteries we have explored together tonight, may be stepping stones to conceptions of reality we cannot yet imagine. In the face of these cosmic enigmas, we might be tempted toward either arrogance or despair. Arrogance in assuming that our current theories are nearly complete, needing only minor adjustments to resolve these puzzles. Despair in concluding that some questions are simply beyond human comprehension, that we have reached the limits of what we can know. But there is a third path, one of humble curiosity, of persistent questioning, combined with deep appreciation for how far we have come. This path acknowledges the limits of current knowledge without assuming these limits are permanent. It celebrates each discovery while recognizing that every answer raises new questions. It values the journey of discovery as much as the destination of understanding. As you continue to relax and drift towards sleep, consider that you are made of the same elements forged in the hearts of stars, elements scattered by supernovae explosions billions of years ago. The carbon, nitrogen, and oxygen in your body once existed in stellar furnaces. The iron in your blood came from stellar catastrophes. You are, in the most literal sense, stardust contemplating the stars. More than that, you are the universe becoming aware of itself. The same cosmic processes that produced galaxies and solar systems eventually led, on at least one small planet, to the emergence of life, consciousness, and curiosity. The atoms in your brain, following the laws of physics and chemistry, have organized themselves into structures capable of asking about the origin and fate of the universe, about the nature of space and time, about the deep structure of reality itself. This capacity for wonder, for reaching beyond immediate concerns to contemplate cosmic mysteries, represents something profound about human consciousness. In our questioning, we transcend our biological origins, connecting to something larger than ourselves. We participate in a grand tradition that stretches back to the first humans who looked upward in awe, and forward to generations yet unborn, who will continue this quest with tools and concepts we cannot yet imagine. The universe does not owe us answers. The cosmos unfolds according to its nature, indifferent to our desire for understanding. Yet in our asking, in our persistent, methodical questioning, we express something essential about our own nature. The questions themselves become a kind of answer, not to what the universe is, but to who we are. Curious creatures on a small planet, looking outward and inward, seeking connections and patterns, meaning and understanding in a reality that continually surprises and bewilders us. Some of the mysteries we have explored tonight may be solved in your lifetime. Others may require centuries of scientific progress, new mathematics, new forms of observation, new ways of conceptualizing reality. A few may lie permanently beyond human comprehension, cosmic koans that can be approached but never fully resolved, mysteries that can be lived but not solved. In either case, there is a profound beauty in the questioning itself, in the reaching beyond what is known into the vast territory of what might be. In this reaching, we grow. We expand our understanding, our imagination, our capacity for wonder. We become more fully human by embracing the mystery that surrounds us, neither retreating from it in fear nor claiming to have mastered it in arrogance, but dwelling within it with open minds and hearts. As you drift now into sleep, carrying these cosmic mysteries with you into dreams, remember that the same laws of physics that create black holes and expand the universe also allow for the emergence of consciousness, of curiosity, of the capacity to ask about the deepest nature of reality. The same cosmic processes that seem so mysterious from one perspective have produced, through their precise operations over billions of years, beings capable of wondering about them. There is a profound unity beneath the apparent duality of observer and observed, of mind and cosmos. We are not separate from the universe, but an expression of it, a way through which the cosmos experiences and explores itself. Our questioning is the universe questioning itself. Our wonder is the universe wondering at its own existence. Rest now in this mystery, this paradox of being both the questioner and part of the questioned. Let the cosmic puzzles we have explored tonight inspire not anxiety but peace, not frustration but wonder. The universe does not owe us answers, but it offers questions like stars, countless and luminous, guiding our journey through the vast night of the unknown. Sleep now, in the space between understanding, in the gentle embrace of cosmic mystery, where questions themselves become a kind of answer, and where not knowing becomes not a failure but an invitation, an opening to greater wonder, to deeper participation in the ongoing story of the cosmos, a story still being written in the language of stars and galaxies, of space and time, of matter and energy, and of minds that dare to ask about the nature of reality itself.